Yes, the topic for today is physically based flood modeling and artificial intelligence perspectives. Artifact is the project which started in October last year. It's about artificial intelligence for flood resilient infrastructure. There are 4 partners in the project. You can see our logos at the bottom of this slide. The project is led by Institute for Artificial Intelligence in Novi Sad in Serbia, with 3 other partners. TU Delft, where I come from the Netherlands, IHE Delft, also from the Netherlands, and the Hamburg University of Technology. It's a 3-year project. It was funded under the Twinning call, some of you may be familiar with. And here is you can see the website here if you want to learn more about the project itself. Now, the objectives of the projects are twofold. The first aspect is research. So we are really trying to advance artificial intelligence in urban flood modeling, primarily in 2 directions. The one is the AI-driven urban flood modeling for short-term flood prediction and generally for flood prediction and flood risk assessment. And the second one is future flood proofing using nature-based solutions or blue-green infrastructure technologies. In addition to research, the project has a strong capacity building component. That's the key aim of the Twinning proposals. So the key knowledge transfer here in this case is supposed to happen between the 3 Dutch and German partners on one side and the Institute for Artificial Intelligence in Serbia on the other side. And we are aiming to advance the Institute's innovation capabilities by increasing capacity in all these things that you can see here on the screen. Of course, it's not a single way. Capacity increasing and learning. Artifact will also advance other partners' capabilities. So we are trying to basically help the predominantly artificial intelligence experts that exist in the Institute for Artificial Intelligence in Serbia learn a bit more about engineering and flooding. And we are also hoping in the process to learn something from them about artificial intelligence. An integral part of the project is a series of expert training events, which are designed to enhance skills and knowledge in flood risk assessment and so on, and facilitate knowledge transfer between partner institutions. This will be done as a series of workshops, 6 in total, 2 per year. And this is the first such workshop. And today we are focusing, as I already mentioned, on physically based flood modeling. Veljko, do you want to tell us a little bit about who registered for the event today?
Yes, thank you, Zoran. So as Zoran mentioned, the purpose of the project is to establish expertise of the 4 main institutions within the project, but we want to be inclusive, and that's why you're all here today, because we don't want to hoard the knowledge. We want to share the knowledge with everyone. So we invited broad audience today, and we will for all future 5 events, as well as the summer schools that we are holding every year, once a year. And some of you might have seen these summer schools calls for this year's summer school in Novi Sad. A little bit more about that at the end. But for today's training, we had 45, well, a few days ago, we had 45 registered participants. It's mainly from Serbia, as we are hosts, and it is expected. But yeah. But we have a nice spread from across the globe, from Canada, Australia, Germany, India, UK, France. So we have all the most continents here, as I see, which is great. Most people today come from education and research, so universities and research centers. Well, we have some consultants and government officials and software developers as well, who have joined us to learn about this topic. And we have also asked your background in water engineering and AI. And while most of you are experienced in water engineering, you expressed the desire to learn more about AI, which is great. Well, today's topics are gonna cover partially those topics, but we are more today focused on water engineering. But please stay tuned for the upcoming 5 expert trainings, which are going to focus more on AI as well. You can go to the next slide. So we also asked what your expectations are. And yeah, so obviously flood and AI have been the key words. There was a lot of hope, hope to learn, which hopefully will deliver on your hope to learn more stuff. So we had some responses that you're interested in how AI and flood modeling, urban flood modeling can be integrated. We're going to touch upon that today, and a lot more in our summer school and a lot more in upcoming expert trainings. And we had one respondent who wants to learn everything. Well, I'm not sure that we can teach everything in the next 4 hours, but we'll try as much as we can. But thank you all for joining us today. Hopefully it's going to be informative for you. We'll have a section at the end where we answer your questions. So we want to have interaction at the end as well, and learn more about where you come from, your perspectives, how things are done in your countries, which we're looking forward to that. And for any housekeeping issues, you can message me in Zoom, or Milan, or real Milena Tamburic, which I'm not sure now which one is real. So final thing for the newly joined, if your name is not Milena Tamburic and you have joined as one, please just change your name. I see still 3 Milena Tamburic. So if you can change your name so we know who you are when you decide to talk to us, it would be great. But in the meantime, enjoy the lectures, and yeah, thanks.
Thank you, Veljko. And this is my final slide. This is the agenda for today. So after this brief introduction by Veljko and myself, we will have a couple of lectures by Professor Zoran Vojinovic from TUHH Delft. After that, we'll have a bit longer break for lunch, about 30 minutes, and then we'll look into case study examples, which will be presented in 2 further lectures by Zoran and by Natasa Manojlovic from Hamburg University of Technology. And then at the very end, we will have these questions and discussion session that Veljko just mentioned. So please stay tuned until the end. In terms of questions, if time allows, we may allow 1 or 2 quick questions following each of these lectures. But the idea is really to try and save those questions for the final session, especially if you have more than 1 question or a bit longer question. Okay, thank you very much. So, Zoran, the floor is yours. Please introduce yourself and give the lecture.
Yeah, thank you very much, Zoran and Veljko. I'll just try to find my sharing configuration here. Okay. Try to put it into the presenters mode. Okay, so now I hope you can see my slides.
You're not in the presentation. Oh, now it's in the presentation mode. Yeah.
Okay, great. Well, welcome once again. Good morning. Welcome wherever you're joining from. The first block of these lectures will be on the topic of the urban flood modeling, and it's going to be really an introduction. I come from TUHH Delft, from the Netherlands, but I also have appointments at 3 other places, which is University of Exeter, University of Belgrade, and National Cheng Kung University in Taiwan. I have 25+ years of experience working in the industry, in the water industry, and also in academia, and my expertise areas are in planning, modeling, design of water, environmental systems, hydrometeorological risk assessment, nature-based solutions, climate change adaptation, and hydroinformatics. I've over the last 25+ years, I've produced over 150 publications and reports, and I've published 4 books. And the 2 books that I will be using, which are reference for these lectures today, are the book which I co-authored with Professor Michael Abbott, on the topic of flood risk and social justice, and the other is the book that I also co-authored with another Professor Roland Price, and that's on urban hydroinformatics, data models, and decision support. So you will find pretty much everything in these two books, and there, of course, there could be some other papers. I've pretty much worked around the globe, not so much in Africa, but in many other parts. And in some of the case studies that I'm going to show today, I will refer to some of these practical experiences that I've gained by working in different locations. Couple of projects, just to mention some of the notable research projects that I've been working on and leading. There is a project called Reconnect. It's still active. We are in the phase of closing it now. It's on the topic of nature-based solutions, where we demonstrated in 9 different locations, different kinds of nature-based solutions for flood protection. And then also before that, there was another, I think, very interesting project, which with the name of Pearl, and that also looked into some ecosystem-based approaches in addition to the modeling. So the learning objectives of this first lecture is to provide you with a basic knowledge concerning urban flood simulation using physically based models, as Zoran mentioned, and I'll try to cover some basic key concepts, and we will show you some practical applications. And we hope that at the end of this, at the end of today, that you might be able to be more effective in applying the new knowledge and supporting tools for flood risk management. So I will first start with some very kind of setting the scene background information. Flood risk community very much connects to the disaster risk, general disaster risk community. And then what you see here is the standards UN expression of the disaster risk, which defines disaster risk as a intersection between the hazards, vulnerabilities, and exposure. So you need to have a hazard, you need to have vulnerability, and then either important assets or people are exposed, and then therefore there is a risk for a disaster to happen. So disaster risk can be expressed as a likelihood of loss of life, injury, or destruction and damage from a disaster in a given period of time. So now we take that definition and we project it to a flood risk, and the flood risk, we can also put it into the notion of that the flood risk is a function of the probability of a particular event. And here we are talking about different rainfall events, and different rainfall events, they have different AEP or ARI, average recurrence interval, or annual exceedance probability. Like 1 in 100-year event has 1% probability, 1 in 10-year event has 10% probability. So what depends which event we are analyzing, that's the probability of that event, and that's the hazard. And then the other component is expected value of severity, which you may find in some more general literature on disaster risk management, which is again can be broken down in different subcomponents. Typical subcomponents are the vulnerability, exposure, but then you also people from the disaster risk community that talk about the coping capacities and resilience. In practice, these 4 terms are very much combined into one, because the coping capacity or resilience on one side and vulnerability are kind of on the other side of the same coin. So the practitioners tend to combine these elements into one. So you end up having the hazards and the vulnerabilities that you need in order to express the risk, the flood risk. So moving to the hazard. So what is the hazard? Is a phenomenon that has a potential to harm humans and or cause a damage to the environment. So it's not it is a threat. It's not the actual event. And as I mentioned before, it can be expressed in terms of the probabilities. Like 1 in 100-year event carries 1% probability. So in terms of the rainfall events, as I mentioned, we can rank the rainfall events. We can, as the hydrologists do, we can take the long records of the rainfall recordings, and then we can use some plotting position formula, for example, Whitehall plotting position formula, and then we can rank these events and then come up what is the typical event for 1 in 100-year interval, for 1 in 50 years, perhaps 1 in 20, 10, and so on. And then these events we can use for the analysis of hazards. So what is important to know here, the take-home message, is that the hazards are always, or almost always, addressed or assessed through the use of numerical models, and therefore the topic of the first lecture. Very briefly on the concept of vulnerability, there are more than 25 definitions that you can find in different literature, and again, the disaster risk community have defined those. It is really, it can be referred to as inability to avoid potential harm. So it is difficult to measure vulnerability, and often the vulnerabilities, they can be the overall dimension of vulnerability can be divided into different sub-dimensions. For example, if you take an urban area, you can break it down into different aspects. You can look into the physical objects, you can look into the assets, the tangible aspects. You can look into the environmental or nature aspects, such as parks, maybe green areas, and so on. Then we can look into the social component. And social component, of course, matters because we need to know, in order to assess vulnerability in a particular area, we need to know who lives there, what is the age, perhaps. Is it the rest home? Is it the school? Is it the area which hosts a number of schools? And so on and so on. So we need to look into the social aspects. Economic, typically, the dimension of vulnerability refers to the economic sector. How quick or how resilient or how vulnerable is the economy of a particular urban area, and how quickly it can bounce back following a disaster. We can also come up with more dimensions, such as institutional. We can look how different institutions, like the emergency services or health sector or some other services, how do they react in case of a disaster? So, and then we can estimate how these vulnerabilities are present in a particular area. And then what we usually do, we can express them in the form of a raster or a vector file in the GIS. And I'll come back to that. This is what I like to show to my students, that if you have a guy who is working under the truck, like this guy here, obviously he's a vulnerable. This is a very simplified illustration of vulnerability. Maybe here also you can find some people who are more vulnerable, some other people might be less vulnerable. If you look at some other cases, again, we can try to see that if people do things that put them in danger, so obviously, and if they're not protected, they are vulnerable. And I can go on like this. This is a classic example. If you see this kind of picture where some people are busy with some maybe chemical, biochemical problems, and then you come along and unprotected, obviously you're vulnerable, unless this is the university exercise where the guy in shorts is a professor and the others are students. So we can go on like this, but the bottom line is that the risk can be decomposed into different components in order to assess it for a particular area, and in order to come up with some flood protection measures which will minimize the risk. We talked about this part. Now, again, the important distinction on how do we estimate hazards is by the use of numerical models, and this is what we are going to talk today. And while the vulnerabilities, coping capacities, resilience are typically done through surveys, interviews, or some other kind of assessments, but not necessarily the use of models. So the models are, particularly computational models, are used for the assessment of hazards. Now, before we move on with the modeling, what is very important is to distinguish different types of floods, because different type of floods has a different physics, different propagation properties, and of course, you might need to consider certain aspects in your modeling work, and that may differ if you have pluvial or urban flood or fluvial. Flash floods are typically the fastest occurring type of floods that come from steep slopes, from hills. Could be a coastal flood coming from a coastal system, groundwater, or sometimes you may also have a combination of two or more of these types of floods. So now, for example, if you have a picture like this, where you have a river and you have a large area that's been flooded, then the question is which type of the flood is here. We are not in a lecture room, so I cannot ask this question now because I'm going to waste a lot of time on going out and inviting people to comment. But I'm pretty sure that you can conclude that this is a fluvial or riverine flood because it occurs along the banks of the river. If you have example like this is my favorite example is the Cuba, Havana, and Havana is situated on the coast. So this is and often floods. This is the road called the Malecon, and obviously this is an example of a coastal flood. Okay, then if we have, as I mentioned before, steep slopes and hills which generate fast runoff that comes down into the low-lying areas to the valley, that is typically referred to as flash floods. The difference between the flash floods, fluvial floods, and in some cases fluvial floods is that the velocity of the flood or the physics of the floods can be considerably different. Obviously, the flash floods, the velocity can be 3, 4, 5, 6, 7 meters per second, whereas typically with the riverine floods, the propagation and the velocity is much slower. So this is a flash flood. I've showed you before the coastal. Now this is an example of a groundwater. Groundwater floods. If you happen to have or see the floods in a basement of a house, that typically would come from a groundwater, we would call it as a groundwater flood. And of course, you can have a combination of these floods. This is an example of a pluvial flood, which is a result from the insufficient capacity of a drainage system, and therefore the drainage system, which may be comprised of the pipes, sometimes open channels or combination of the two, maybe will start showing a surcharge on the top of the manholes. So talking of the flood hazards, and again, the models are used for flood hazards. Typically we distinguish 4 variables that can characterize a flood hazard. Models compute typically the water levels, velocities, duration of a flood, and if you turn on the advection dispersion component, for example, you can model the water quality processes and the concentration of pollutants in the sediment transport and things like that. So depending on the physics of the different flood type, you will choose different variables, which will be computed by your numerical model to express flood hazards. So if you have, for example, if you're dealing with the flash floods, maybe for you will be enough or sufficient to use the water levels of computed depths in combination with velocities to express the flood hazards. And then this is an example how you can do it in GIS by defining different ranges, and then you can put some different levels like a low, medium, high, very high, or extreme. And usually these ranges are based on some studies, and I'll show you briefly some of the work that I've done with my colleagues in Australia when I was living and working there, and also show you a couple of things what the Japanese people are doing in that regard. The final thing that you can also incorporate is the concentration of pollutants, which in areas, for example, I've used example of Bangkok, where I worked quite a bit in Thailand. The Bangkok is quite flat, has a flat topography, and the flood depths that may occur on the roads and the footpaths sometimes may be 10 to 20 centimeters, in which case people would contemplate to walk through these waters as opposed to if you'd have half a meter or 1 meter depth. So if you just base your flood hazards in the sense of the water levels and or depths and velocities for the flood which results in a 10 or 20 centimeters depth, you may end up painting all these pictures, nice GIS maps with some very low to medium hazard ranges. However, if you add the concentration of pollutants and knowing that in Bangkok you have a combined system meaning that the one pipe carries 2 components. One is the stormwater runoff, and the other one is the wastewater, foul water. So so basically you end up having a raw sewage, almost raw sewage on the ground, on the surface, and that floats. And then obviously if people get in contact with it, they will contract some health issues, public health, the diarrheas are typically outbreaks in such situations and so on. So if you go just by the water depths and velocities, then you would not really represent the hazard, then you may need to also consider the concentrations. If you're dealing with the fluvial systems, with the propagation of the again, I can use example of Thailand. In 2011, there was a great Thailand floods event that occurred. The flood water remained between 2 and 3 months on the ground, with some depths of 2 to 3 meters in some parts of Thailand. In that case, you would obviously look into the durations, and then it is up to you how you paint the flood hazard. But these are the variables that normally come from the numerical models. This is something that when I lived and worked in Australia, we came up with this kind of ranges that we used for which specify the depth and velocity, and we tried to relate them to the actual physical situation where the low, let's say 0.5 meter of depth and 0.5 meter per second velocity is really still just suitable for cars, and that's what we called low hazard. And then progressively going with a greater depths and velocities, then we've delineated between the low, medium, high, very high, and extreme hazards. So and this is an example of Bangkok, which I told you that a hazard map, if you just use one variable, for example, a flood water depth, you may look in one way, as opposed if you add duration, or you have a duration there, or if you also add the concentration of pollutants. In this case, we looked into the E. coli concentration. So it is really to be very careful what you choose to take out of the numerical model to express your hazards. So what happens at the end? You have your whatever depths, velocities, durations, concentrations, flood hazard, you compile them all, overlay them, and then you get a map in GIS. So this is about the hazards, and this is why we need to use numerical models. Very quick example of a case where just to illustrate this concept, I'll move now from Thailand, go to Caribbean. This is the island of Saint Martin, which is under administration of France and the Netherlands. This is how the island looks on a nice day. However, and this is the administration border between the France and the Netherlands, for the two territories. And this island suffers from tropical storms. And in 2017, there was a big hurricane that passed through the eye of the hurricane, which was assessed to be the biggest ever hurricane in the history recorded. That was the Hurricane Irma. So the eye of the island went through the eye of the hurricane went through the island of Saint Martin and brought devastated damages, because it brought the speed of around 300 kilometers an hour, but also a lot of heavy rainfall. So what we have done, this is just an example to show you how the numerical models can be used for assessment of such events. We have here, I'll show you, we have here modeled the actual pressure and wind fields and the storm surge, and this is how the hurricane propagated. And on the other hand, we've modeled also the impacts on the land, and then we looked how the resulting rainfall also causes floods. So in this case here, we've used a combination between one-dimensional and two-dimensional models, which I will explain in a bit. So we have also, as an interesting sidetrack, we have also used the similar models, two-dimensional models, to compute the tsunami effects for the same island, because there are tectonic plates just north from Saint Martin, which are known to cause some earthquakes and tremors, and that may cause some hurricanes. Then you can also use the, sorry, not hurricanes, but the tsunamis. And you can also use the numerical models to assess the effects of tsunamis. So this is an example how we combine because it's a flash flood. I mentioned to you it's the water depth and the velocities are very important, because the flood duration is not so significant. Within 1 hour, the flood clears up. But computed water depths can be plotted like this, just showing the depth. This is a combination, the result from 1D, 2D model, one-dimensional coupled one-dimensional, two-dimensional model. This is the velocity profile for the same event. And then if you combine the two using what I just mentioned before, this kind of ranges, then you can come up with presentation of hazards for different events. This is, for example, for one in 10-year or 5-year event, 10-year event, 20-year event, 50-year, 100-year. Then you can go to some extreme events. And then you can overlay that information with your vulnerability, in which case we've used here, we did assessments, on-the-ground assessment of some critical buildings. And we have come up with some kind of a flood risk map. So this is the introduction, just to set the scene and explain the importance of numerical modeling for flood risk assessment, because it really drives the estimation of hazards. So when we talk the urban drainage simulation, it's really, we're talking about the modeling of minor and major systems. The minor system is really the system which is a pipe network below the ground, or the major system is the system that consists of the overland flow paths. And then, of course, you may have the interaction between the main minor and major system, or primary or secondary. In Australia, they call it minor major. In UK, they call it maybe primary secondary. Or in the literature, some people refer to the same dimensions as a below ground and above ground. But the interaction that may happen is through some either manholes and some kind of connecting points, or maybe gully pots. So the flow domain can be either one-dimensional, two-dimensional, or three-dimensional. And then on the basis of whatever we are studying or we want to model, we can couple these models in a usual format, which is 1D model, where we are modeling a minor system pipe network through the 1D model, and the overland flow paths we can model again through the 1D model. So that's why we would couple 1D or refer to that approach as 1D model. Then you may have 1D model, where the 2D model is used, two-dimensional model, for modeling flows along the surfaces, overland flows. And then if you really have a big need to incorporate a three-dimensional model, maybe you want to look into the vertical distribution and how the maybe flows go into the weirs or some particular structures, then you may introduce the three-dimensional model. So the types of models that can be used, we distinguish between the stochastic, deterministic. Stochastic obviously have some random character or random features. In hydrology, there's a lot of randomness. Hydrological, in the literature, you'll see people talk about hydrologic or hydraulic models. Sometimes you may see a distinguished representation through lumped or distributed models. Then in terms of the type of the model, what we also at some point called the data-driven models is perhaps what also has been referred to as artificial intelligence, but we may also have a rule-based models, like using fuzzy models, where we set up the rules. We can also have fuzzy, of course, physically based models, and we can also have a combination of these different models, which we would like to refer to as a hybrid. The models can be also conceptual or process-based, can be simplified in terms of the dynamic equation or momentum equation, where I will come back in a moment into different components of that equation. So we can simplify it, use it through kinematic wave, or we can use it as a full dynamic wave. The models also you can find in the literature, people talk about a low resolution as opposed to high resolution. Low resolution means that the computational points are few compared to the high resolution, where you have numerous, many more computational points. We can also have a model which replicates the flows through sewer system or surface flow or coupled models. Also models we can distinguish between those that are commercial and also the models which may be built in-house for research purposes typically. At IHE Delft, we use commercial models, and we use models from DHI. From Denmark, we also use models from Deltares, but we also have built our own in-house models. And again, you can have one-dimensional, two-dimensional, three-dimensional models. So in this particular class, we will be talking about the deterministic, hydraulic models, which could be either lumped or distributed. It will be, I'm talking particularly here about the physical-based models, process-based, full dynamic, which can be either at low or high resolution, and I'll touch upon on models that are either one-dimensional for the sewer system flows, or those models that are coupled between that use 1D and 2D models. And I will also talk about the examples I'm going to show here today. They're pretty much commercial, although there are a couple of slides from our in-house models that we've developed. So why do we bother with modeling? The models are typically used to, if you want to design a new system or redesign, or you want to optimize some rehabilitation measures. If you want to assess the damages for emergency management, flood risk analysis, I mentioned hazards are based fundamental, models are fundamental for assessment of hazards, real-time maybe management, real-time control management, RTC, support to emergency services, uncertainty, pollution, I mentioned before, climate change impacts, effects of urban growth, and so on. So for all of these questions related that I mentioned here, we would need support from numerical models. So what data is needed to set up a model? Of course, you need rainfall data. You need if you're talking about particularly about the two-dimensional models, we need the digital terrain models, or contour lines, or digital elevation, or digital surface models. We need information about land users. We need information about the drainage system that we normally would use to set up into the one-dimensional model, which can be either detailed, that means that contains every single pipe that we have, but that's very rarely done. Usually, every model of a pipe network system is simplified to a certain degree. So we omit certain pipes and manholes, and then we focus only on the main trunk sewer lines. We also need observed flood events. Why do we need observed flood events? We need it in order to calibrate the models. So why is calibration needed? Is in order to adjust model parameters so that the model can be brought to predict more events that are closer to the reality rather than just some arbitrary results. We may also need some socioeconomic data for damages, insurances, traffic, and so on and so on. The mode of simulation with the models can be either online, so you use it, you're running the model right now, maybe you're receiving information from the numerical weather prediction models about the upcoming storms, and then you want to simulate the model that will predict to you water levels in your system, which you may in turn open the sluices and maybe gates and things like that to regulate the system, or maybe engage emergency services for evacuation or whatever dealing. Or you may have offline simulation, so it's no real-time simulation, but it's really running the simulations for the scenario analysis for the future. And the duration of simulation, every model may give you may take a different time for simulation, and that depends on the system, on the size of the system. Are you modeling 5 pipes or 5,000 pipes, or are you modeling a system which has no structures, pumping stations, overflows, or maybe a system that has hundreds of overflows and pumping stations? So then obviously the complexity. And then, of course, if you're running one-dimensional or one-dimensional, two-dimensional model, so all these things will drive the duration of your simulation, but also the hardware of obviously the processor speeds and all that will be driving your time. So now the flood modeling approaches, as I mentioned, you can do one-dimensional, 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 one-dimensional coupled with a two-dimensional. You may introduce three-dimensional models as well. So if it is one-dimensional model, on the left side, you see what's happening through the pipe. The pipe may surcharge. Some of the software, like DHI software, will compute the volume that comes out from the system, but it will basically reincorporate that volume that comes out back into the system. Whereas if you use the US EPA SWMM software, that will the volume that will be the surcharge will be eliminated from the system. So there are differences between different packages that you may find, but nevertheless, the flow is one-dimensional, and it's just along the X. Let's say if you assume that the X-axis is the dimension where the flow computation goes. Then you may have a 1D model where the pipes are connected to the streets, maybe overflow paths. Then typically the connection between the below ground and above ground is either through weirs or orifices. If you have a 1D, 2D model, then obviously for the 2D model, you would need digital terrain data to set up the two-dimensional model. And of course, then you will couple it with the one-dimensional model, which is used for the either pipe network or the open channel flows. And then you may have also some combination. If you have some rivers and coastal areas, you may have also combine it in a different way. So the a take-home message is that there is no perfectly accurate model. So models and all the modeling work is never accurate, and I put it in with apostrophes. And that's because the models are really a representation or approximation of the reality, and all depends on the assumptions and also on the complexity and resolution of the model, whether the model is going to give you results which are with the reduced uncertainty or with the large uncertainty. And in terms of calibration, the calibration is a very important process because that drives the adjustment of model parameters. And if the model parameters are not adjusted, then the model, if the default values used, it may be appropriate for some area, but maybe not appropriate. Most of the time, it is not appropriate. And then you may get either over prediction or under prediction. So if you're using your model for design purposes, and if your model is over predicting, then you will over design your layout, and which may lead to unnecessary expenditures and everything else. So to minimize these issues, you need to really pay careful attention on the calibration. And the calibration is as a process which requires measurements, the real world measurements, which I'll be talking about this in the second hour. So those measurements are used to compare with the model results, and then through a trial and error process, we adjust certain parameters. There are parameters on the hydrological side of the model and also parameters on the hydraulic side of the model that we need to adjust. And then we try to merge the two curves together, which is the modeled and observed or measured. Or we can also attempt to use optimization techniques such as genetic algorithms, which can, in a rather automatic fashion, perform this adjustment of these parameters, and then you press the button and you leave the model to go through these iterations until the parameters are kind of picked by the optimization technique. So if this is an example of the model result versus the gauge, meaning measured. So I have on some events my model is predicting well, on some events is not predicting so well. Then I would contemplate to do my calibration work and then perhaps bring these two curves more closer so that I have less error on my predictions. So now the question is, how do you know when to stop, when these differences are acceptable or not? What we need to do, we will need to use some statistical error functions. And in terms of I mentioned before that in Thailand, you have a combined system where one pipe carries two flow components, the wastewater and the stormwater. The sequence of attempting calibration, it goes through the first, we need to perform the dry weather flow calibration, which is related to the flows coming from the wastewater points, sewage and so on. And then we would attempt to do the wet weather flow calibration. And the wet weather here refers to the particular response of the system to a rainfall event. So first we'll do dry weather and then for a combined system. And then what we need to also be very careful is that when we look into the errors, when we study the error of our model, when we calibrate the model, but then we need to study the errors, we may track the temporal, seasonal biases or magnitude biases. Temporal and seasonal biases are the biases that occur throughout a particular period of time or particular season. So maybe a model is constantly over-predicting or under-predicting during the wet season where the groundwater aquifer comes in, and maybe we are not incorporating hydrological model of the below ground surface to a great level of details. So then we need to be careful to track for this type of biases. Sometimes the bias can be a magnitude bias related to either low flows or high flows. Maybe your model will be predicting very well on small events, but not very well on the large events, for which you need to perform some additional rounds of calibration. And then you may also plot residual plots between your errors to detect these biases. I mentioned that that you can use different statistical formulas to look into the error of your model or the accuracy of the model, and then that really there are different functions that you can use, and I happen to be studying that as part of my PhD some time ago, where I looked into different distribution of noise and different range magnitude, and then of course there can be different functions that can be used: root mean square error, coefficient of determination, coefficient of efficiency, Pearson's coefficient, and so on. And then I happen to have found one particular function which was least dependent on or kind of least influential from different conditions, but you can use a standard statistical formulas. In terms of the calibration procedure, in hydrological side of the model, we would first adjust the mass balance, looking into things such as the runoff coefficient and things like percentage of impervious versus percentage of pervious. And then we would go through the adjustment of the timing of the peaks. So that's for the hydrological part. And I mentioned that with the hydrodynamic models, we have two components. One is the hydrology, which is a rainfall runoff, and the other one is the flow through either pipes or open channels or overland surfaces. So for the pipe flow models, which is very much the hydraulics, we can have the different approximations, and in hydrodynamic software, we typically use the shallow water equations, which are the Saint-Venant equations. And what you see here is the one-dimensional expression of Saint-Venant equations, where we have the top equation is the conservation of mass or continuity equation. The second equation is the momentum or dynamic equation. And that equation, of course, has a number of different terms, which can be, again, when you run some of this software, particularly this commercial software, that they'll give you an option. So the first term on the left side is the local acceleration term. Then you have the convective acceleration. Then you have the pressure term. Then you have the friction and the slope effects. And depending on your approximation that you want to use, you can distinguish, you can eliminate certain terms, and you can run your model as a kinematic wave or diffusive or dynamic wave. What is very important, or take-home message from here, is that if you are dealing with floods, then you should be better off to work with dynamic wave and do not contemplate to use the kinematic wave, although computationally is much faster kinematic wave, but it is really comes down to the Manning's equation, which is not really influenced by the dynamic conditions such as backwater effects and flood issues. So another good reference, as I mentioned, I have these two books that all these things addressed there, but also another interesting reference, maybe this article that was published some time ago in Urban Water Journal, which goes through all these assumptions of these different equations and also talks about how these equations are solved. Although that you can find also in the two books or any other book, basically, that talks about the hydrodynamic models. These equations are basically the hyperbolic partial differential equations, and they cannot be solved analytically. And for them, you need to discretize the domain in terms of the time and space. And then through the discretization, then you can use different solving methods, such as the finite elements, finite difference, and so on, in order, and these equations are solved numerically, so through the iterative processes. So for the pipe flow, calibration procedure involves looking into the Manning's number nodes in terms of head losses and also in terms of the weirs. Simulations can be either design criteria approach or event-based simulations or time series. We take the whole series of rainfall data and you simulate. In terms of the accuracy, and I'll finish in a few minutes for the first block, inputs are usually not very known, and we have to be aware of that all these models, besides the uncertainties due to the system and geometry of the information that we enter into the model, there is a degree of uncertainty there, but there is also a degree of uncertainty due to different other sources that provide inputs into the models. And these are some of them. And also what is important to know, the sewer systems change in time, the pipe roughness change. So if you have a pipe that was constructed 50 years ago, then obviously you need to, which was maybe with a certain material and has certain roughness value, you will need to probably run the CCTV camera or something like that to look at the condition of the pipe and then try to express that in terms of the roughnesses. So I will skip this part. In terms of the software, I mentioned there is a commercial, typically is the DHI software, and DHI software is a software where the numerical engines are written by the Professor Mike Abbott, the late professor who was a professor at TUHH Delft, and I had a great privilege to work with him and co-publish one book with him. So all these DHI engines are powered by the Mike Abbott's numerical developments. And on the other hand, we have also software from, I put here on the slide, Deltares, which is another big lab for the hydraulic modeling software. You can also find other, like Bentley nowadays as well, which is a different company from the cars. And you may find other software through the US EPA, or maybe you can find also HECRES software for one-dimensional modeling of rivers, and so on and so on. I think I will need to go for another 5-10 minutes into the next block of lectures, just to finish off the modeling steps. So I may need another 5 or 10 minutes. So I think we are now about on time to have a break, 5-minute break, if I'm correct, Veljko or Milana.
Yeah, we can take a break. Quick break now, so you can refresh as well. Thank you, Zoran.
I don't know if this is not designed for any questions, eh? So questions will be at the end.
Yeah, I mean, yes.
Yeah, that's the idea, yeah.
If you want, you can take some quick questions.
I'll leave it because, you know, I'm also cautious. I have quite a few slides to show, and I will go into the second part of the lectures. So I would not, unless there is a really couple of, there are a couple of super burning questions, then I could take them. Otherwise, we do it at the end.
Okay,
so, yeah.
That's good.
Okay, can you see if there is any hand raised for the super burning question? Or maybe feedback. Am I going too fast? Is it overwhelming for colleagues? I saw that almost everyone said they have some kind of knowledge of water engineering. So I assume that they can go a little bit fast.
Yeah. This is not at a very basic level. No one is. There's not many people that have no knowledge.
Okay.
So I think it's good.
Okay, so no comments. I hope people didn't chase away people. So, but let's have a 5-minute break, have a coffee, and then we come back.
Sounds
Okay,
good.
but we are already running 5 minutes late. So yeah, please keep it to 5 minutes. So back at 11:05.
Yeah. Okay. I will quickly switch off my camera to go make myself coffee.
Okay, it's 11:05, so I'm assuming people are back.
Yeah. Okay.
So please continue, Zoran.
Yes, thank you. I will. I mentioned before about the hazards and how the some people are very serious about it. I'll show the example. What's the how our Japanese colleagues are looking into that test. So, for example, I will play this one. I hope you can see what I'm showing here. This is a test carried out in they do this quite a bit in Japan. When you talk about hazards, different velocity of the water, different depth, and of course different circumstances will affect abilities of people to walk through flooded areas. This is an example from Japan, where in urban areas, particularly vulnerable spots used to be, not any longer, but used to be the metro stations, where the water will run down, gush down through the stairs, and then the people who are trapped need to walk out. And this gentleman is showing that it's not really easy to walk through that. So by doing this kind of studies, you can you can really, and this is again another one looking at the underground in Japan, and they are pumping the water and kind of checking to see how the people can pass through. And this is very important because when you need to delineate between different ranges of hazards, then you can see you can see the effects and the impacts. Another examples, again, stairs, pumping water down the stairs, people walk through that. And even there was an interesting case where they've looked into how different depth of water will impact on the possibilities to just open the doors. This is the 40 centimeters of water, and if you're trapped in a house or in a flooded area, then you won't be able to, you might not be able to open the door. So it just gives you perspective on how to look into the hazards and how to think about the different ranges of the hazards. Okay, now I will move to the part of the flood modeling and what are the steps, how do we go about it. And I have here lectures for both open channel flow and the pipes, but I'll just pick the pipe thing. So what are the steps?
Oh, okay. We can see now,
Yeah.
Now it's fine, yeah. Now it's fine. Go ahead.
I think it takes a couple of seconds to just come up. So what are the typical steps if you are about to conduct the flood modeling study for a particular area? Obviously, you start from getting the thorough understanding of the project objectives, and sometimes the project objectives may influence selection of your model, of your data resolution, or data collection campaign and everything else. So I think it's very important to be clear, and particularly if you are working as a consultant for your clients, to understand what is driving the flood modeling study. Then, of course, when you want to build a model, which is, as we said, approximation of a reality, so it's a numerical approximation of a real world, it is very important to go and perform the site visits, to look into different parts of the catchment, look into different structures if there are, maybe look into some pumping stations, overflow structures, and so on. So that helps a lot when you want to reproduce that in a digital world in the model. Then on the basis of the objectives and on the available data, you would plan maybe additional data collection. And then when you perform that, then you will obviously analyze your data, because sometimes you may have some further gaps, or maybe you have some inconsistencies, you need to clean it. And that's, I like to put it again, the question, understanding of project objectives, and maybe on the basis of the data that you have on the situation that you inspected, you may need to refine your project objectives. And then these tasks will ultimately lead you to the selection of a particular model in terms of the type of the model, and also because application, it's going to drive that, but also in terms of the resolution of the model. Is it going to be 1D, 2D model, or is it going to be maybe a model that will also necessitate another model, three-dimensional model? After you decide on the model, then you will go obviously into GIS. Typically, we go to GIS to delineate our catchment and sub-catchment boundaries, because we go with a hydrological layer analysis. So then we will set up the hydraulic, and maybe pollution variables or parameters into the project, into the model. Then we may perform the kind of dummy tests runs to see how the model is working, and then potentially to perform further data cleanup. Sometimes you may have a negative slopes in the pipes, adverse pipe diameters, where the pipe goes from a smaller, larger, then back to the smaller diameter. So these kind of things, maybe you want to triple check, and your model may report some errors. So when you've cleaned it up, then you obviously would install some sensors, instruments that we'll talk in a moment, and then you will collect some flow, velocity data, water level data, and then you will perform the calibration and verification, which we talked a few minutes ago. And then once the model has been calibrated, and if you're happy with your with the accuracy of your model, so to speak, then you may decide to progress to the next step, which is why you're building the model in the first place, to perform simulations and to process the results, if it is design, if it is whatever application. And if I need to illustrate this, let's go look into the how to set up a model for which is comprised of the pipes. So first we will go, as I said, to following thorough understanding of the objectives and following the site visits and a selection of the model. We will then go to GIS, and then we will perform the catchment analysis, hydrological analysis. So we will look into the highest elevation and define the catchment boundary. So if I would have topography like this with a lot of hills, then it is a nicely delineated the catchment boundary, which you can look from the top, and then this is how the same catchment would look like from the top-down view. This is from the side, top-down view. Then the next step is to perform sub-catchment delineation. So we need to go into the smaller aerial units. Every GIS, particularly if you use ArcGIS, there are so many hydrological functions there, which will, in the matter of 2 or 3 steps, help you to delineate these sub-catchments. And then you may get your sub-catchments. They may look like this. So the sub-catchments are really areas where the sub-catchment boundaries represent the highest elevation point in a particular given area, which means that when the rainfall occurs, that the rainfall will the runoff will go towards the kind of low-lying areas within this area. So there will not be a runoff going between one sub-catchment to another, rather than it will just drain down. And then the next thing is to overlay that with your pipe system, and the pipe system will have obviously pipes, and will have also some manholes. So the next point for you is to give the identification to each and every sub-catchment, and also each and every manhole or the node in the system. And then it is for each and every sub-catchment, we have to calculate the various hydrological parameters depending on the hydrological model that we are using. Typical parameters are the impervious percentage of imperviousness, slope, maybe type of soil, which will also drive processes such as the infiltration and so on. Depends on different hydrological model. You will collect different data for each and every catchment. And then you will need to define the loading points. So the loading point is the point in the network, or the node in the network, which will receive the flow coming from these sub-catchments. When I mentioned the governing equations for the hydrodynamic models, which are the shallow water Saint Venant equations, and we looked into the form of one-dimensional equations, where one continuity and one momentum equation. Obviously, if you have a 2-dimensional model, it will be 2 momentum equations and 1 continuity. What we saw there is that these equations, they're hyperbolic partial differential equations, and they require boundary conditions. In order to be solved, they are designed for the subcritical flow conditions, not for the supercritical flow conditions. So sometimes the conditions in the pipe flow system will change from maybe supercritical, going gushing down the flow, going along the steep slope, and then going to the flat valley. Then you have subcritical flow conditions. So this software will typically not be able to compute the exact physics of the hydraulic jump that will occur between the supercritical and subcritical flows, but it will pretty accurately compute the upstream and downstream conditions from the hydraulic jump. And the way because the software is not designed for the supercritical flow conditions, it's designed for subcritical, having one boundary condition downstream and one boundary condition upstream. So what is happening in this software, when you have supercritical flow conditions, then at least that's what's done in DHI and Wallingford software. the so-called Havno approximations are used to reduce down the terms in the momentum equation, and depending on the conditions, shifting from supercritical to subcritical, and this is where the slopes are very important, because different conditions will drive different flow regimes. So in terms of the modeling inputs for a system, for a pipe network system, so we need the geometrical data, system data, obviously manhole and pipe data. We need hydrological, I mentioned rainfall, hydraulic. If we want to go into the advection, dispersion, and water quality process, we may need concentrations, advection, dispersion coefficients. If we are looking into sediment transport, then we need to look into what type of cohesive or what kind of sediments we have, what is the size, and so on and so on. So when we set up this data, typical pipe flow data is comprised of the nodes or the manholes and the pipes. For the nodes, the typical information, we need the X and Y coordinates of the nodes. We need the inward and ground levels, inward being the bottom, ground level or the top. We need the diameter and standard diameter of the manholes for the pipes, which is less than 1 meter. Diameter is 1 meter. For the larger pipes, maybe 1.5, 2, and maybe larger pipes, you will need you will need a chamber, and that chamber will be with the special dimensions, which also need to be taken into account when you set up a model. But if it's just a smaller pipes, regular pipes, which are most common, then you will be just putting the information of 1 meter diameter for the manhole. In terms of the and then of course for the pipes we need the diameter of the pipes. In terms of the if we are setting up a two-dimensional model, then we will obviously need the airborne laser survey or contours to be used, to be interpolated in a GIS to create a raster representation of the surface topography. And this here illustrates that you may have one-dimensional model for the pipe network and two-dimensional model for the surface flow, where we couple these two models, and there is a exchange in momentum and information and the water levels between the two model domains. And 1D model, when it gets surcharged, passes on that information to the two-dimensional model, which then computes through the cells how the water propagates, and then the water can also come back to the pipe network. So that dynamic interaction can occur, and it can be computed. In terms of the two-dimensional model, a couple of words that we should be aware of. When we talk about the digital terrain model or digital surface model, or some people call it digital elevation model, we can have a representation of a bare earth, which is just like there are no objects, no buildings, no roads, no anything. It's just the bare earth interpolation, which is on the left side, or you may embed the road network. In some places around the world, I've seen that the people use the road network as a dual drainage system, where the curbs are quite high, and they're used really to convey the water as well as a kind of additional system. So in that case, you may need to really incorporate, because the streets may act as channels, open channels. So then you need to incorporate maybe roads into your DTM, and this is the representation in the middle. Or you go to the representation where you also incorporate the heights of the buildings or the buildings themselves. And then this is what we have on the right. And obviously the flow directions on the left side, if it's a smooth bare earth DTM, the water can go anywhere it goes, depending on the elevation, everywhere, from the higher cell to the lower elevation cell. In the middle, where you have roads, obviously the water will be confined to the roads until the moment when the curbs are overflowed. And then you have in the right side, the water will not obviously get into the building, it will go around the buildings. But that is important, because when you take the two-dimensional model results to express your hazards, then you need to be really careful about the hazards at the building points. If you incorporate the buildings, then maybe you need to be careful how you express, because the depth can be different at different side of the building. It's not impossible, but just something to be careful. Another important point is that when it comes to the 2D model setup, we have to be aware of different features. And example here is if you have a elevated sort of infrastructure, such as the sky roads or sky trains, then if you take the data straight away from if you're running the airborne laser survey, which we will talk in a moment, you will then get a big wall. Or maybe if you have an arc where the water can go underneath, you may also end up introducing a wall into your two-dimensional model, which will again give you incorrect representation of the flows and the flood maps. Or maybe if you don't do proper filtering of the green infrastructure or the trees and things like that. Or sometimes if your resolution of a DTM is, let's say, 10 meters, which in the past people used a lot, 10 meters. But then if you have 1 meter gap between the buildings where the water can pass through, then obviously you will not capture this type of openings. And then again, your flood map can be different. So what I'm trying to say here, not only that the model can bring in inaccuracies or uncertainties, but also the data drives that a lot. And the buildings can be represented in different ways. You can use you can elevate the buildings, or you can induce the roughness values. I'm not going to go through this. Or you can use sometimes there are methods based on the energy loss footprint and the footprints, or you can use buildings as you can model buildings as porous elements. And yeah, one of the colleagues, Vincent Guinot, former colleague from IHE, who now lives and works in France, he has done a lot of research in terms of the porous elements, using the modeling buildings as porous elements. And there are other methods. So I will conclude now with a couple of more slides that just to show you that we have to be very careful when we perform airborne laser survey. I had a PhD student who had looked into all these commercial filtering algorithms, and obviously when the guy who does the flyovers and collects the airborne laser survey point cloud data, he will need to process this data or run through this data through a particular filter. So, and there are different filtering algorithms, and I can tell you that all these filtering algorithms can give you potentially different flood maps. Here's an illustration of 5 1D, 2D model representations, where the 1D model is the same, 2D model differs in terms of the representation processed through different filtering algorithms. On the left side, you can see this kind of shaded light area is less, which is a flooded area. It's comparatively less to the expression and in the middle, where it's a much wider area is flooded. And again, it's different from the other image on the right side, and then different from the image below. So when you really take a detailed analysis, you will find that these different filtering algorithms will drive your flood map representations. So something to be aware of. And the very last thing about this one is that when we build a 2D models, again, the resolution plays important role. This is an example of a model that they've taken off from Dhaka, from Bangladesh, with just one area of 7 hectares, just to illustrate the difference when you use different grid size for the representation of a 2D model. So now what we can see here, we can see buildings, we can see the edges of buildings. We can also see, if you pay close attention, you can see the curb lines and the roads. So obviously, if I use this representation for my 2D model, the water will first be confined to the roads when it spills from the pipe network system, or if it doesn't get captured by the pipe network system, will start flowing in a confined way along the roads. And then when the curbs are overtopped, it will start approaching the buildings. However, if we have a 2-meter resolution of the same area, you can see how the edges of the buildings are smeared, and the curb lines are becoming less prominent, which means that the water can be spreading much more easily around, eventually giving you different flood map. This is a 4-meter resolution of the same area. You can see that the smearing is even more prominent, and the curve lines are completely wiped off, so the water can really move left and right. With 8-meter resolution, 16-meter resolution, the water can be really anywhere, pretty much. 32-meter grid size, because I picked this one because I know that some people used to use SRTM databases with 30 meters for the whole world. It's something to be very, very careful when you get your flood model results. 64 meters and 128, no feature is evident. So if you have 5 meter, 10 meters, 15 meters resolution, obviously, depending on the topography, the 5 meter will give you maybe reduced flood extent as opposed to 10 meters or 15 meters. And if you are using, let's say, 15-meter model with a 15-meter resolution to the measure model, and if your pipe, if your critical infrastructure is shown to be flooded, in actual fact, if you use high-resolution model, which we assume that the physics is more accurate, you will not find that the critical infrastructure is flooded at all. So it's something to be aware of. And again, the references for these lectures today are contained in these 2 books, and also there are some papers. So I would like to thank you for your attention for this first block of lectures, and I will now move into the second block, which is the and I will need you to confirm to me if you can see my opening slide.
Yeah, we can see it.
Which is on the topic of data collection for urban flood modeling. These are the slides that I've developed together with my colleague and friend, Ole Mak. He used to work for TUHH. He's from Denmark. So it was part of our lectures that we are giving. So I picked up this. I have quite a few slides. What I'm going to do, I'm going to skip through some of them to fit with the time. And I think we have to finish off this block by 11:45. So we have about
15 minutes.
15 minutes, yes. Okay. So I will be flicking across a little bit faster to some of it. I would like to I would like to define or distinguish between the data. We may call them temporal data, because if you install a sensor in a particular pipe network system or open channel network system or a rain gauge, this is the data that will, when you fix the time step, you may get the data being recorded every minute, every 5 minutes, every 10 minutes, every hour, every whatever. But it's a really temporal kind of sequence. So that's why we can refer to that type of data as a temporal data. On the other hand, we may also have another category of data, which is a spatial data. I talked a lot about the terrain data just now for the 2-dimensional models, but also there comes the geometry or system data. But also, if you're dealing with the coastal systems, then it comes into play bathymetry. And this is what we're going to be covering now: data processing for flood modeling. Again, same references. I don't need this big introduction here. I will jump immediately into the instruments. How do we measure flows? Well, we can use different techniques, different instruments. We can use sensors and meters. We can construct the structures in pipes. We can also use some portable devices. There are different things. And what is usually measured is the depth or water level, velocity, and then the quantity is computed. Nowadays, you have these type of surveys getting quite affordable. And by the way, I have a cat here. So if you hear occasionally a little meow, that's my cat. So the contractor who would perform these kind of surveys would process the depth and level data, velocity data, look into some maybe noises and all of that, and would try to express that maybe into form of a quantity or Q, discharges. And sometimes we can opt to use very simple technique just by using the ruler to measure the depth. Sometimes you may opt to use the pressure sensors, and then maybe sometimes you may use the ultrasonic sensor. I'll go through a very, very basic aspects of this. So the ruler or the depth of stick, depth of flow stick meter is really of a limited use, because you cannot stand with that kind of thing with a ruler for hours and record the depths. Obviously, you can do it it's a single reading, and it may not be accurate because you may have a debris at the bottom of your domain that you're measuring, and which means that you need to clean it properly if you want to get more accurate readings. In terms of the pressure sensors, they measure the difference between the water and air pressure to determine the flow depth. And obviously, they're very sensitive to the flow that covers the sensor, the actual sensor. So they have more reliable readings when there is a greater depth than the readings when you have a very low depth, which is kind of going even below the sensor itself. Readings may drift and it may require recalibration. And obviously, pressure sensors are sensitive to the conditions in the system, in the gas, because in the sewer systems we may often have a gas of different kind composition, and we may need to perform some air ventilation of the system. This is an example of a pressure sensor for a flow meter, and they have some. Obviously, all of these instruments, they have advantages and disadvantages. As I mentioned, too low flow is hard to measure, and sometimes you may have a loss of power and things like that. Ultrasonic sensor, which is typically installed typically for the pipe network system, it can be at the bottom, but can be also at the top of the pipes, at the soffit point. It measures depth and measures the airspace. If it's at the top, measures the airspace above the flow. And it uses the sound and reflector. So it has a transmitter which sends the sound signal, and there is a receiver which gets the signal back, and it measures the time of return, and basically recomputes that in terms of the depth. So we all know that the signal is, the human hearing is between the 20 hertz and the 20 kilohertz, whereas the ultrasonic signal is a 40 kilohertz, and so it is beyond the range of human hearing. I'm not sure if my cat will be able to hear it or not, but this is what happens for the humans. So ultrasonic sensor can be often affected by the noise, because it is a sensor that relates to the sound. So if you have a big construction works on the road, you need to really be careful with your readings and installations, signal direction, and this is how it gets installed. So if you have a pipe, you may have your metal ring with some, you position your sensors, either pressure sensor or ultrasonic velocity sensors, and then there is a logger further up, goes to the cable, and then the logger can sit in your manhole, or you can take it out of the manhole to another chamber, which is kind of prevented from the vandalism, obviously. But usually it sits in the manhole, and then the data from there can be transported. You can either go physically to the site, connect with your computer, or you can get it wirelessly transport through your telemetry and SCADA system to your office. So this is how it works. I mentioned that it has a transmitter and it detects the echo. On the left side here, you see a picture of the ruler depth of stick flow meter. This is an example of, I took a photo, this was in Bangkok, in one of the pumping stations there. So the guy who operates the pumping station, he would record particularly the water levels at a certain period of time. These other things are different velocity pressure sensors. And then what you do, you mount them on this kind of metal ring. You position them there, then you, depending on the diameter of your pipe, you insert it into the pipe, and then there is a cable. And then you can, as I said, you can either come and physically download this, or you can receive it through the wireless system. There are different problems with ultrasonic sensor. I'm not going to go into these details. All of these instruments, they have different advantages, disadvantages. You can also use electromagnetic meters and so on. This is the velocity sensor. If you have a flow cross-sectional view of a pipe network system with a manhole, then you have two crystals. One is the transmitting ultrasonic signal, and the other one is receiving it back. So why is this important? It's very important to carry out these surveys, this kind of measurements, so that you can get the data in terms of the flows. But at the same time, we would like to always install a rain gauge in the vicinity of our flow gauge, so that the rain gauge can get the corresponding rainfall data. And then once when you record this, then you can open up in Excel or whatever data processor you have, and then you can look how the rainfall looks in relation to the flow records. And that can already help you a lot, but then further step to use that is for calibration purposes. I will move on because I have another 7-8 minutes to go. Okay, this is very important. How to pick a location where you want to install your instruments. Well, the different locations will set your instrument to either be more erroneous or to be more accurate. If you're picking a location which is close to a particular bend where the pipe turns, let's say 90 degrees, due to the head losses, and if your gauge or sensor is installed very much in the vicinity of that bend, then it may be affected by the velocities that make you shoot in all different directions. So you need to be aware of it. Also, if your installation is where you have a steep slope going to the kind of transition between the supercritical and the subcritical flows, then again, due to the head losses at the particular transition, you may get also problems. And obviously, you will try to avoid where you have problems with the structural integrity of pipes when you have some cracks and things like that. So broken pipes, obstructions, drop connections is another thing. If you have heavy inflow infiltration, slope changes, if you bend turns, velocity changes. Okay. Another important thing is to mention here, if you ever get to do this type of survey, you really need to be very careful how you approach confined space entry. And there are always procedures for that because going into confined spaces such as sewer systems, you have hydrogen sulfide and you have other gases, sometimes methane, even explosive gas. So what you need to do, you need to really put the test the situation with the gas, concentration of gases in the system, and then ventilate if necessary, and then wear appropriate wardrobe and equipment in order to do that. I've known people when I worked and lived in New Zealand who were very experienced to manage this, to do that. They were very confident. They were entering the sewer systems on daily basis for so many years. However, it is just the moment when the gas can overcome you, and then you can have a problem. I knew this chap, Ken Carew from New Zealand, who was very capable guy, but yeah, he was not careful once, and that costed him a life. So obviously you may need to look some vaccinations, and you must be careful when you lift your manhole covers because of the weight that they carry. Then I will now move into another thing. Yeah, when you measure the rainfall, we typically use the tipping bucket rain gauges, which is the bucket there that when it gets filled, it tips and sends the signal. So you know that how many tips are there, so you can relate that to a depth that fell. But very important aspect there is that you take into consideration spatial variability of rainfall. So what does it mean is that if you are performing a catchment study where you're building a model, you want to calibrate the model, where you may have, this is my data from one of my projects in Australia, in Sydney, Belmore South, for example, where we had 3 rain gauge systems. You can see how they are widespread. There is one in the middle of the catchment, the other one on the eastern side, and the other one on the southwest. So now I have plotted below 3 plots, which represent the measurements taken at these 3 different rainfall stations. So what we can observe here is that the second and the third rainfall station have pretty much similar, not the same of course, but similar distribution of rain, whereas the first one does not capture some of the big events. So obviously there is a moving storm that passes through an urban area, and depends on the size or the size of the urban area. You may have this spatial variability more influential. The problem if you just have one station and you want to use that station measurements for your model calibration, but then you might be, especially if it is a condition like in this Belmore South measurements that we had, you will be put on a mission impossible, because your model will be forced to predict something that's not been measured, and then you will get into a problem that you will not be able to explain your results. So very important is to take into consideration spatial variability of rainfall. Now, a few words of the spatial data collection. two-dimensional models, they require terrain data collection, which you can do either through the ground surveys using a level meter or the theodolite or the total station to measure this. And then you take the spot elevations and then you can interpolate and create continuous surface that you can then later import into your two-dimensional model. But then nowadays, the technique called airborne laser survey is getting very, very convenient and affordable, which require basically a low-flying aircraft, which has a GPS system that talks to the satellites at the ground positioning station, and it has inertial measurement unit, and it has also LiDAR scanner, which is the light detection and ranging, laser scanner, which sends the signal to the ground and measures the time of lapse and when it comes back. And obviously, different surface will have different reflectance capabilities, properties. And the guy who flies around will pick up all elevations, including the geomorphological, the morphological objects, the greenery, and also some buildings and everything that he passes through. Then when he's finished, he need to perform the morphological filtering. So he needs to take out, obviously, for the water, especially for the flood applications, we don't need to know about the heights of the buildings. And sorry, not buildings, but the trees, morphological objects. So what we are after the bare earth in this case. So these type of measurements from the morphological objects need to be filtered out. And then this may look like this. You may need to interpolate, and then you create whatever domain you need. For the pipes, obviously, the pipe network system, you need to perform the physical survey. You need to open the manholes. You need to put the level meters. You need to measure the heights and everything else. And you may also need to be aware of that the pipes that you may model can have a different shape, cross-sectional shapes. So it can be circular, can be O-shaped, egg-shaped, or any other shape, depending on the system. If the system is very old, it maybe have if it's a brick sewer, it usually has a egg-shaped profile. Most of these PVC pipes nowadays they have a circular shape, but it all depends on the conditions. We talked about this information in a previous class, what we need. And also, you need to collect the data about your maybe pumping stations. You need to know what's your is it the pumping station that has the pump which is submersible, which has maybe wet well, and then you need to have characteristics of this wet wells. And then, of course, pumping station is defined through the QH relationship, and that's what you enter into the model. Another important aspect of the drainage systems is the amount of water it's going to get into your pipe system depends on the number of gullies and how they're distributed along the roads or the catch pits or cesspits or catch basins, whatever people call them. So you need to also be aware of those. Combined sewer overflows, separate sewer overflows, very important structures. We need to pay a particular measurement way how to measure them. Sometimes you may have a combination of open channels and closed conduits. So the previous discussion was about the pipes, about the open channels. You obviously need to get the cross-sectional areas, and you may have culverts, and also you may have bridges, and which also sometimes are very important, depends where they are, and because they can act as a restriction to the flows. In case you have retention or detention systems, you need to know the area, you need to know the depths, and these things can be reproduced in the model. This is an example of a sports field in Porto Alegre in Brazil, where it acts as a dual kind of purpose area. In dry conditions is the dry, in wet conditions acts as a storage. So you will obviously need to know the geometry of these kind of systems. This is another example of similar thing from Denmark. I took photo. The last thing I want to mention now is for the models, when you collect the data, we also, besides the geometry of the system, we also need to pay careful attention on the condition assessment. So when it talks about the pipes, you may need to run the CCTV surveys to get the idea of what is the condition, structural integrity of your pipe, and how does your pipe look inside, and what sort of roughness coefficients you need to put in. because it is not always the all ideal as we may assume. This is we need to also be aware of the illegal connections. This is the picture, for example, I've taken from from Australia, from Sydney. You may think that everything is well regulated in Australia, but no, you can find some illegal connections. People stick their house pipes into the nearby manhole, which may be separated, and then they put the stormwater connection, and then it's a problem. So I would like to finish it off here. And again, I don't think we go into questions now. We go into the questions at the end of the day.
Okay, thank you, Zoran. Yes, I think we can allow one quick question if someone has a burning question and they may not be able to stay after lunch, so they want to ask now.
Okay, sure.
Any such question? Just unmute yourself and start asking.
I hope I didn't chase
Okay.
away.
No, it's all fine. Okay, that's fine. It seems we don't have such a question, so let's leave all the questions for the final session of the day. Thank you, Zoran, for both lectures. We will break now for lunch, so please be back at noon at 12:15.
Yeah.
I'm going to share the agenda on the screen so that everybody can sorry. Yeah, so that everybody can see what is going to happen after the break as well. Veljko, you wanted to say something or no?
No, all good.
Okay, well, thanks. Have a good break and see you in about 25 minutes or so.
Okay, see you soon. For culture and so on. So I will quickly, there is a publication that came, several publications that came out. This is one of the recent ones that looked into the effectiveness of small and large scale nature-based solutions, but in combination with some hybrid solutions for the Ayutthaya Island. So these are examples of these objects that you can see. They're quite monumental, where you cannot really apply the classic the depth damage analysis type of. So this is where Ayutthaya is. If you see, this is a map of Thailand. Bangkok is south, and Ayutthaya is about 2 hours on the north to drive. It's surrounded with different rivers: Chapraya, Pasak, and Laburi River on the east. And the island is well, in that particular year in 2011, there were 5 storms that consecutively happened, and they brought a lot of floods to the local population. And I mentioned in my previous lecture that the water remained on the ground for 2 to 3 months, and in some parts it exceeded 2 meters. So this is the Ayutthaya. Again, a lot of monuments there, but it's kind of the areas are scattered. There are also some residential pockets. I will skip this stakeholder analysis part because it was very important for us. This is in terms of the hazard assessment. Because the area, this area which was studied falls within the catchment of Chapraya River. And Chapraya River is a very, very large river, which we first modeled using the one-dimensional model. In this case, again, it was Mike 11. Then, and this is what you see on the left side. So on the left side, so you can see, first we have a full model of Chapraya River. Then we have taken one part to the right side shaded area as a second model. So we have taken the boundary conditions from the first model and used in order to simulate the second model. And then what you see as a shaded area on the second model represents the area where we coupled 1D and 2D model. Why we didn't couple 2D model with 1D model at the first step? Impossible, because then we would need to take an enormous land surface area, and computation would be very much impossible. So then we had to do this kind of nesting and come down to the format that it was manageable for simulations. So what you see, so the shaded area on the second image is the extent of the 1D, 2D model on the third. So we would consecutively run the model 1, provide the boundary conditions to the model 2, and then after running model 2, provide the boundary conditions of the model 3. And yeah, these are some of the results. I will quickly finish, I think in 5-6 minutes. I just want to show you some of these results, if I can, through some simulations. Yes. Okay. So what you see now here is the simulation concerning different scenarios. On the left side, on the top left corner, you can see these rivers that I was talking about. It's Ayutthaya Island. They call it island because it's surrounded with the waters. And that area has a dike, ring road dike, which goes around this region and prevents these monuments from being flooded. But in 2011, the water was so much, and the blue shows the flooded areas. So when I play now, you will see how the water propagates for that particular event in 2011, and quickly overtops the dikes around and gets into the again, if you just pay attention to the okay, I'll pause now, to the top left corner. So this simulation shows the current situation without any improvements. If this event would happen again, or this is how it happened in 2011, the entire region would be flooded, even though they implemented a dike and all kinds of other measures. This area will be devastated. Then on the next, to the right side, the image shows the implementation of few measures, and then to the right, few more measures, and then few more progressively. And we did calculations, cost-benefit analysis for all these measures to present to the local stakeholders so they can decide. So you can see that the first top left corner, do nothing scenario, shows flooding of a great degree. Then small implementation measures would make some areas dry, but not everything. And then if you kind of progressively implement more and more flood protection measures, then you can see the difference. So in this way, it was very, very effective to use this 1D, 2D model results to communicate some of the findings to the stakeholders and to get them to actually participate in the selection of measures. In terms of the vulnerability, I just mentioned this with a couple of slides. In terms of the vulnerability, we've looked into again, this was discussed with the local population and the stakeholders. We had 23 community groups and plus ministry and UNESCO, because this falls under UNESCO heritage and other players there. So with them, we discussed what would be the 4 dimensions of vulnerability that we need to take into consideration. So we've identified physical, social, cultural, economic, and then we've kind of merged them all together. The methodology for that was we had a large survey, large-scale survey for the social vulnerability, looking into different vulnerable groups, flood awareness, income, insurance, access to insurance, all these sort of important aspects for the social vulnerability. I need to go back to this. And then we try to map it, in GIS. Then the next thing was to look into the physical vulnerability, look into the buildings. And here we have identified 3 types of buildings. In Thailand, in this region, they have the so-called pillar houses. Obviously, the predecessors who lived in this area, they knew that this area floods. So they used to build these kind of pillar houses with the piles. For these people, they're quite kind of, they really have a very low vulnerability level because they're high up. They have even boat, which is tied to one of these pillars or poles. And then when there is a flood event, they can quickly come out and then they can go from A to B relatively easy. As opposed to people who live on 2-story houses, for them, the ground floor would be trapped and damaged. The upper floor would remain intact. And you have also houses which are 1-story house, which will be completely flooded. So for those houses, we developed the so-called depth damage curves. But then the challenge was to look into these cultural properties, these monuments, and how to come up with the vulnerability assessment of those. And this is the cultural dimension. So this is for the depth damage curves for the properties, for the houses. But then the cultural, more of the social, economic vulnerability, but look into the economic sector, different businesses, how quickly they can come back. But this is an interesting point because it's quite novel back then. We looked into, with ICOMOS and UNESCO people, we talked and developed a method that we can express the vulnerability assessment for these objects so that we can there is no time now to talk about this, but we have some publications. Who is interested, I can provide the reference. And we try to map it. And then basically the final result is the combination between the social, cultural, physical, and economic vulnerability to get the overall combined vulnerability. However, and then the idea is to combine with a hazard map. However, after mapping the vulnerability in this way, or the risk in this way, computing using numerical models, 3 different models that we use to produce the hazards and then this vulnerability combined, we produce this kind of risk map. Then we went to interview the people, local residents, to see, do they actually feel the same way as our study has shown? And then, to our surprise, we found that in some areas we did not overlap. So we had quite some differences in terms of the what we came, and this is what we call the risk perception. So interviewing so many community groups and different residents, we came to the point that the risk calculated versus perceived, we call this calculated through the model and everything else, was significantly different. And what we decided to do, we've taken the so-called perceived risk as a target, and what we have done with our calculated risk, we have adjusted vulnerabilities, the different weights of vulnerabilities for different dimensions, so that we can reflect the so-called perceived risk. And then we've used that model for the assessment of measures. And in the assessment of measures, we have used all kinds of small-scale, large-scale nature-based solutions. And that approach worked quite well. So with this, I would like to finish off. And just the idea of this lecture was to show you how the models can be used effectively in combination with other types of assessments to assess the flood risk and to propose some rehabilitation or flood protection measures. So I think I'd like to finish off here and pass the floor to Natasa.
Okay, thank you very much, Zoran, for a very interesting presentation. I can see that questions are popping up in the chat, which is nice to see. We won't be answering those yet. We will wait for the Natasa's talk first, and then we will we'll start looking into those questions. But please keep those coming for the later on session. Okay, thank you. So Natasa, the floor is yours.
Thank you. Thank you. I hope you can hear me well.
Yes, we can.
Yes, that's fine, because I have a new laptop, so I've checked, but it's always good to check again in this room. I will share in a minute, just a second. Let me just find yeah. Also welcome from my end. I mean, to this this meeting, an online expert meeting, the first one. We've heard quite an extensive introduction, and thank you, Zoran, very much for covering basically everything and all topics. And my role will be to address some further aspects, within a case study. And first, would like briefly to introduce myself. I'm a senior research associate at the Hamburg University of Technology, and working in the field of river and coastal engineering, mainly in urban flood risk management and assessment, but also management of the hydrological risks. Also, one of the topics I'm working on is related to nature-based solutions, and that's one of the topics, of hybrid solutions. And there was actually the time and moment when within the Reconnect project, when also together with Zoran, we could also explore potential for demonstration and upscaling on different nature-based solutions in different areas along across Europe, but also worldwide. I'd also like to mention another project, which also is related to what to the topics we are talking about. That's the national project called TUHH Klima. And that project explores the future perspectives of the flood risk management in the Elbe estuary. This is the estuary where also the city of Hamburg is located in. And due to the sea level rise and the climate change, we'll have different flooding situations along the estuary, but also including the Hamburg and very densely populated urban area. And we are exploring different types of solutions, from gray to, less gray or kind of grayish, up to the green ones, assessing them from different perspectives, also including the cost assessments. trying to see, at least to indicate in which direction flood risk management of the city of Hamburg, but also of the adjacent areas can develop into. But apart from that, I also looked at all the topics that are supposed to be addressed, or they're expected to be addressed here, and pretty much was covered by the lectures of Zoran today in the morning and after lunch. There are also some topics that I've identified and that I think would also be good to address them. One of them is risk, which Zoran already addressed very nicely. So my presentation will also relate and build upon what he has presented, especially in the last case study. There is someone who wanted to learn everything, but also integration and practical solutions, also from the institutional perspective. So the practical aspects and how all that what we are doing, how it's actually coming and being used by the institutions, it's also something which we have to address, we want to address there. So where is the potential also for the implementation, but also we look also into the direction of how we can merge all that what we are doing also further, and what are the further potentials for implementing digital twins or the means of the artificial intelligence. So I would like to give a bit the German perspective. So my case study will be located institutionally, I would say, in Germany, with a focus on the northern Germany, but we'll also present some cases or some of the issues. It's not going to be one case covering everything. It's going to be more covering some of the aspects and issues which are also related and are to be addressed when we are talking about urban flood modeling and management, also including the risk. And we'll make also some final remarks on that. Flood risk has been already defined here and addressed from different perspectives, and Zoran introduced it also in his opening lecture. And even it's defined, I mean, like there is this kind of a generic perspective of risk. I mean, for flood risk, also there are different definitions which are also anchored in different laws and legal documents. And for example, the German water law says that it's a combination of the probability of occurrence of a flood event with the possible adverse consequences for human health, environment, cultural heritage, and economic activities and significant material matters. This is rather, that's open, I mean, comprehensive and quite generic, but in practice, what happens very often is that we reduce it to the monetary terms. It's like when you, especially working for institutions and working for any kind of client who wants to have a clear situation about the flood risk, first thing that is being done, and very often here in Germany as well, is left at this monetary level, not going and exploring so much different dimensions like what we had with the social, institutional, and cultural. Although this is something which is done on top, but we still have, I mean, this kind of generic definition reduced to the concept of the failure or the probability very often. Especially in urban areas, it's also looked at the failure mechanisms and the failure of the gray infrastructure or the infrastructure that is in place, that is doing the defense, particular dikes and walls, if you're talking about the fluvial floods, but also computed or kind of done multiplied with the damages, and in the end we get this risk which is expressed in monetary terms. I mean, like put in a very, very simple terms. This can also be applied as a concept for different settings and different types of floods. For what we had fluvial, but also fluvial floods, we just have different infrastructure and very often different than probabilities and failure mechanisms, if we consider them as well for the analysis. But if we want to describe the vulnerabilities and the part which is related to consequences, very often we start at least with the damage functions. So that's a concept that, I mean, already has been addressed. And here I would like to also say something about the experiences which are kind of encountered here in Germany and how things are being done. I mean, if we look at the modeling and we look at the physical modeling and physical assessment of floods from the perspective of what is being done with those results and where they actually land and end up with which kind of analysis, what we are doing with that. So what we have here is that in Germany, at least, there is a kind of a body of representatives representing all federal states, and they come up with recommendations and guidelines for different aspects of water resources management. And also there is a kind of a guidance document and recommendations for the reassessments of the flood risk and risk zones for the implementation of the floods directive. That will be the third actually round of reassessment. And this time there are also some novelties or some kind of additional requirements or ideas that should be done and should be implemented, so that all federal states should at least consider that and actually explore the possibility. And because it's a recommendation, whether this is something which can be implemented in this way, or we stick to the kind of already existing practice and repeat the third cycle with the same methodology that was done and that was used before. That also includes the models, and because we have different requirements, you have to see and revisit the set of models you're using. That also includes the hydraulic and hydrodynamic models, but also the risk assessment. And one of the things that is happening now in Germany is that all federal states should consider to take and to use the BEAM data set from Copernicus as the background, is actually the basis for all kinds of developments and modeling work of risk that has to be done there. So it is, I mean, a question whether this is something that will work. So there is no experience when it was recommended. And different federal states started using that for flood and risk modeling and gathered some experience, but each federal state should make his or her own decision. I mean, like, it should be something which is at the federal states level with strong idea and strong encouragement to unify the method, so that there is a kind of a common background and information which is the basis then for different comparison, different analysis that should be conducted there. But we do the flood risk assessment. There are different scales of analysis, from the macro scale, which is at the level of a province or level of a kind of a larger district area. We scale it down to a medium scale, which can be an urban district, for example, or we can also have, even more detailed assessments, the micro scale, where we do topology of the buildings, like what we had in the case of Ayutthaya, and derive or damage assessment concepts specifically for those types of buildings or those types of objects that we have there. There are some examples of those generic functions that are being used in Germany, for example. That's from the area of the River Rhine, or suggested for the River Elbe. And they are widely in use and being used actually in cross-referenced across Germany. But in the LAVA document, we also now have suggestions or recommendations what kind of functions we should use for different data referring to the BEAM dataset. So there is a list of those functions, and is also strongly recommended and encouraged by the generic body which is, governing the LAVA group, to use them and to apply them to all the assessments of all countries. So there is a kind of a family of different damage curves, which we already know. I mean, they actually relate the damage rate, so they are relative damage functions, to the water depth. And that's how they are then being used and expressed. But in order to do a risk assessment, practically what we are doing, if we use the model data, we combine the data related to hydrology and hydrodynamic actually modeling with all the asset values, and they are combined and mapped using different damage functions, and we get actually specific net damage per spatial unit, depending on what kind of spatial unit we have. Usually it's actually the water raster, like water depths, which are then imported or taken from the hydrodynamic models, then combined and intersected with the land use. And then we have this mapping function, which is the damage function, or the set of damage functions which are then mapping the value of a raster cell to actually a specific damage. And that's being then done for different annualities of the recurrence intervals for the flood events. And then we have a set actually of those functions. In order to use a value and then this value in the end and later on for the cost benefit and for the further processing, we average that and then get a value called the expected annual damage, which is then being further processed and analyzed for the risk classes. And also in the end, what is happening actually is that there are risk classes that are defined and they are given for different types of areas here in Germany, very often, especially in the area like we have in Schleswig-Holstein. It's a northern province of Germany. There are different classes and defined for the urban and non-urban area. So just to emphasize this difference and not using the same criteria, same threshold value for the analysis. The LAVA document and the idea is also to use and to have kind of rules for the threshold, and one of the rules, and that is also very often being used, is if the damage of the wetted area, of the area that is flooded, is less than 5% of the all net asset value of the area, of the region, or the administrative units that is being then regarded to, then it's considered as a not significant damage or not significant risk. Otherwise, it falls under the banner of a significant risk. And all that is now being implemented, and knowing that, I mean, like to have it as a final result in the area of Schleswig-Holstein, which I've already mentioned. It's the northern part of Germany, and the northern state of Germany, which is now in the process of the reassessment of the flood hazard and risk maps for in focusing on the 4 catchments, which are also urban, peri-urban, and rural. But particularly interesting is actually the urban part because of the challenges associated with the data and modeling and data accuracy or uncertainty, which is then to be considered and taken into the account. I would just like to go briefly to some of those methods which are we using. Sorry, I will just pass here. And for that purpose, actually, we are using a modeling platform, Calypso. We were talking about and heard quite a lot about the commercial software, which are widely in use and well known, and a very high quality and accuracy, having excellent support and already proved in different settings, geographic, but also in terms of the size of the catchment or the size of the area to be modeled. And here we have a platform which is an open source platform available at the SourceForge, which has different modules from Calypso hydrology up to the Calypso risk. So it's going through the whole process of the implementation of the floods directive and supports the development and the production of the flood and risk maps. It's available at the SourceForge, so it can be downloaded and then used. Of course, they are not the latest development. There was a release a few years ago, a year ago, but there are also some further latest developments which are then done for particular cases or clients like what we have now in Schleswig-Holstein. And first model, that is then being used is the Calypso hydrology, which is then, going through the phases of model setup, calibration, result, basically pre-processing, processing and post-processing. That's, you have to start setting up the model, and that's how that looks like in Calypso. So basically, it's subdivision into subcatchments. Then you analyze the soil and the land use parameters and define the so-called hydrological responsive units, as it is a it's a deterministic model and it's a semi-distributed model. And then for all those units, actually you analyze and assign different characteristics, also including the groundwater, which is then, and of course the network, the sewage network, which I mean discharges in this area, and it's also being included and connected. And in the end, it's being then run. The model has been run, and with the long and short-term calibration, the model is to be then calibrated. As an outcome, we get the discharges of different annualities, which are then are going into the river itself. So it's an input for the hydrodynamic model, which is then being used, and it's being developed. I mean, like there in the Calypso, there are different tools, I mean, supporting the hydrodynamic models, 1D, 2D, and 2D model. It's also being used together with a telemac, so that the modeling itself can be performed also for, I mean, using the 1D and 2D with the telemac. And then the telemac actually calculates the water depth, the two velocity components at each point of the calculation grid, which is given here. Finally, the outcome of the hydrodynamic model is a water level raster for different annualities and recurrence interval for the flood, referring to the flood events. And all that comes together into the Calypso risk module, which is a standalone, separate module that is supporting different types of data or background data, which is new. What is new here is that the BEAM dataset is enabled, so it's possible to use and to test the BEAM dataset and check whether all the functionalities and elements that are given there they are really supporting and giving the aspect to or required level of detail for further analysis for the risk assessment. And it's a workflow based. I will just go briefly through the whole structure here, and where we have the I mean, stepwise implementation of the risk assessment, like what we have seen, combining the land use data and which is here. It's in German at the moment because it's being now developed for a German client. It's importing the land use data and basically the background data, and then going further with a import of the hydrodynamic data, so they are being then intersected here. And so that's a view basically which is then being used with a workflow and all the data and scenarios that we have here, and the map view. I mean, like similar to what's given in the ArcGIS, with some tailored approaches and some tailored elements used and developed for the Ministry of Schleswig-Holstein, which I mean they have as a requirement. And after importing the background data, you can also then import the hydrodynamic data and all the flood events. I mean, starting from the 1 year up to 200-year flood events. This is usually what we get as an output. And this data can also be visualized, and we'll see, I mean, like the extent and where is actually, which is the area that is covered by different flood events, different recurrence intervals. And what we also can do in Calypso, and it's going very easy and straightforward, is that this mapping function, which is in this case the damage function, the set of damage functions, can also be imported here. I mean, like the default values are the ones given by Lava, because we are now working with a BEAM data set. And in case some other are needed, they can also be added and changed, and depending also on the need. And finally, I mean, after calculating the damage, so basically for the given water levels and for the information that we have in the background, I mean, like in terms of the net asset values, the flood as first the damage potential is being calculated, which then later leads to the development and the assessment of the risk zones. And then here, I mean, different damage potentials were given for the different flood events, I mean, from the 1 year up to the 200-year flood event. And then that's also then being computed and given as an output as the expected annual damage. So here again, I mean, like you can also visualize different of those events with and without the background map, and also, I mean, get this information. What about the point? I mean, these are the functionalities which you also have in ArcGIS or QGIS that's similar to that. And in the end, you get the flood risk zones. And here, basically, it was just the first assessment. I mean, for the annuality of 1 year flood event, basically everything was green with some red areas, but it gets worse once you get. I mean, you increase the level of extremeness of the flood events. So all the, I mean, statistical kind of analysis, which is done for all those areas, different types of areas is given there. So you can also group, merge, and because we are here in an urban area in Hamburg, I mean, parts of the greater Hamburg, but it's basically physically, administratively, it's still in the Schleswig-Holstein, it's in different federal states. It's also possible to split and to do all kinds of analysis, which is actually, well, quite convenient, but it's also very common and not a special and additional functionality, but it's useful. But what is interesting here, and that's why we are talking about that, I mean, like giving or having the BEAM dataset as a requirement, at least as something which has to be checked. It's the first thing you have to do is to check whether it's still what about its usability? Can we really use it, and the accuracy of the data in general? I mean, like to compare it with a real situation, but it's also about comparing it with the previous data sets, which were already used for the second cycle round of the reassessment of the flood risk, and see what is to be expected, or whether, first of all, can we use this data, and secondly, is it possible to somehow adjust it, or what happens in the end? What about the accuracy and usefulness of this data? And we said, like, BEAM is something which is available at the Copernicus side, and it's using the Korean land cover, but in Germany it's also using the urban atlas. So it's giving also a much higher level of detail than Korean, which we'll also see. But it contains spatial data on the land use and land cover. And what is very interesting here is that it's giving also the net value, I mean, the asset value per category in euro per square meter. And that's something which you don't get in different data sets. So that was the idea, to have this kind of a common kind of repository of data in common database that can be also then compared and used, in this case, across Germany. But this is what happens if you compare the Korean ALKIS and BEAM. So there are differences, and that was the idea to use, I mean, because for the modeling, actually, we need, especially in urban areas, it's important to know, I mean, what kind of data accuracy level you have and what you are dealing with, to compare those data sets and see whether this is really working, and how it can also impact first the flood modeling, I mean, with all the distribution and the propagation of floods, and secondly, also the risk itself. And so there was a kind of a method that was applied using kind of this generated network, or raster, that was then used, and then checked within those raster cells what kind of changes, what kind of land use we have in all three sets, and on the ground. So that was all our kind of validation data set. That was actually the real data on the ground. And I realized that there are some issues with the BEAM dataset. There was a wrong assignment of the polygons. In this case, there were small ones, but in urban areas, it can also be kind of a problem, especially when it comes to assignment of damage functions. They are different for different types of the area, but still, that was something which had to be addressed and had to be somehow corrected, or should be corrected. But also the level of detail. I mean, in the beam, for example, for our control area, there were, there were differently. I mean, here, for example, in beam, there were, 135 polygons in the region. We had here much more in the ALKIS. That was the control data set that was used in the previous. It was, I think, widely used in Europe. And so again, had to be looked into what is different and how does it impact flood and risk modeling. And here we had also the placement of the elements which were either shifted or rotated. So it was a kind of random placement of the elements in beam without having really a physical meaning and physical extent. And there we also kind of reassessed, because the modeling from the rainfall runoff modeling through hydrodynamic up to the risk is now being done there. So there was an issue that had to be resolved also when we had and got the results from the hydraulic modeling and hydrodynamic modeling. But also it's in the hydraulic modeling, I mean, there are also data issues. I mean, Zoran addressed some areas where data are challenged. I mean, the data, scarce data areas where you have to find a way to get data. And here you have data, but sometimes, I mean, their quality is challenging, and it's also creating some problems when you're doing modeling. And for example, if hydrodynamic modeling, you have, different DTMs, which should have the same coverage, but they are scattered, or they look differently, and or they're cells without values. So there are all kinds of things which are still happening, and that's also creates additional challenge to all that what we were talking about. But also the building issue, which was mentioned by Zoran as well. I mean, if you're modeling buildings as the previous and impervious elements, so where is the water level and how you consider buildings. So there are different approaches, I mean, there are different ways. I mean, both were implemented in the modeling activities we had here, depending on the issue that we have. But what is also interesting here, and what we are should keep in mind, that very often when we talk about and we discuss about such kind of problems, where trying to really get very well calibrated model, I mean, like try to get the water levels, which are at the centimeter level. When we do it, the risk assessment, we combine such a kind of high level and high quality hydrodynamic models with damage curves. I mean, in this case, when all the assessments related to damage assessment, it's totally different order of magnitude when it comes to uncertainties, because there are so many assumptions that are being taken when we do the risk assessment, so that they are often overriding all the issues that are given here with the hydrodynamic modeling. And as we could see, the functions are still very kind of simple. We have depth damage curves very often, even if it's important, the duration is not considered, or the velocities, it's very difficult to consider as systematically velocities, because they change, I mean, depending on the velocity, I mean, vector and how it's moving. Along the flood propagation, it's makes difference what kind of object is being then addressed and where and which angle. So it's difficult to really have it as a generic parameter for development of depth damage curves. But also together with the colleagues and the ministry, we've tried to reassess some of those functions to reduce this kind of uncertainty, or a bit increase the accuracy of those data. And sometimes it's not necessary. I mean, like, it's just enough for them for the purpose of the analysis that we have there for green areas, for example, green spaces in urban, but also in peri-urban areas. It's not such a big issue. But when we are in those continuous urban fabric, for example, area, I mean, which is one of the categories in the beam, then it's important to have a good guess. And also within the BEAM data set, because there are different types of urban fabric being represented in BEAM. It's like a continuous and discontinuous urban fabric. They even suggest some correction factors, at least to be used and considered in order to kind of have or grasp this difference between continuous and discontinuous objects there in the area. But that's well, something which is an issue. I mean, like we are still discussing. That's a process where we are going, and at the end of the process, it's meant. I mean, that's how it's also per law here, and also according to the floods directive, those maps will be presented to the people. I mean, living in the area, to the stakeholders, and public hearings and open debates will be open. For the area that we are now kind of finalizing, this area in Pinneberg and the Greater Hamburg, that should be in summer, I mean in July. Maybe that's also the strategy of the ministry to open such a public debate in the holiday season, but actually it is according to the schedule because there is a strict schedule to be followed. So we will have actually experience that from other processes and public hearings that we had in Hamburg for the flood maps, not for the risk maps, but for the flood maps. Then you have the best validation of your model that you can get because people come with photos and counter arguments that if their house is, for example, all of a sudden in the area, I mean, like they will try to prove by all means that they shouldn't be there because of the values of the house is dropping. And so you get actually you reassess in some cases, I mean, like revalidate your flood maps, and if applicable at all, I mean, like sometimes it's just it's not possible. I mean, like the model is right, but in terms of the accuracy and in terms of the level of detail of those maps, so if they are, when the moment they are becoming official, then it becomes a big issue. And there were processes, similar processes also here in Hamburg. I mean, with the public hearings, with the kind of debates, open sessions where people could ask questions, could give counter arguments what we said. Then you actually have to make sure and have to be really sure that your model produced the best value for the input data, that the best value that could be given there, because I mean, every model has limitations and that should be also clearly communicated. And well, for I mean, the whole thing is here in process, and I try to give it a bit more from this risk perspective because it all comes in the end, the risk analysis, and that is a part. I mean, like the flood modeling and all the hydrodynamic and physical models actually feed into such an analysis. I mean, like in this case, I mean, like if you are doing and developing risk maps for also as a part, I mean, like of the reassessment within the floods directive, which every federal state has to do. And these are all the issues maybe to consider when we also develop strategies to overcome that. If we also think about how to use further use and kind of explore the potential to use the artificial intelligence, maybe for this kind of error finding and managing in different data sets. And that's something which is still open, and we have some time also within this project to explore. But in the end, I mean, like what is very often being done, and there are so-called kind of those generic or common platforms where all this information is coming together and is presenting or giving a kind of in a kind of summarized and short version. The possibility to for decision makers to understand and kind of have visualized the different processes, different maps, different analysis that we have in certain area. And here's an example of a planner client. It is a tool where, I mean, the different results, I mean, from different hydrodynamic, hydraulic, or hydrologic models are then put together and are used to make plans for future strategies. I mean, like we were talking about, it's again in German, unfortunately, I mean, sorry, but it's again being done here in Germany. So that you can apply here the natural restoration of river or polder, or kind of the greening of the floodplains, but also measures like in urban areas like green roofs or different swales. The possibility is then enabled to kind of reassess the risk, and in this case was first to reassess the hazard, and starting from the changes in the discharge, I mean, like the nodes of interest, and then to see in which way, I mean, like if we then here, for example, one measure would be, that's an urban catchment in the city of Hamburg. If we green more in the upper stream part, I mean, like in the upper catchment, and place here in the downstream part some small scale measures, some small scale nature-based solutions or LITs, would it be an option for using the big discharge here at the outlet node of this catchment and such kind of things? And that's something, I mean, like which was done at the time as it was developed. It's rather old technology, and using the protocols that were, I mean, applicable at that time, but also the possibility maybe now to use and to enhance the such decision-making process using the kind of possibilities of digital twins and different artificial intelligence technologies. Here is an example of what it can look like. I mean, like you're doing polders or natural restoration of a river, and then because it has, of course, an impact on your hydrodynamic conditions, so the hydrodynamic modeling is being then restarted, and you get different also velocities in different discharges in the whole catchment, and so different types of measures which are given there. So I think based on what we had here, I mean, like now really, I mean, referring to what is happening now within this case study, also talking to German and Northern German institutions, I mean, like there is a need for models and tools to perform such a risk assessment, and there have to be adjusted if possible. I mean, there should be agile way of developing such tools based on the requirements which are given by the institutions. I mean, like for the next reassessment cycle, I mean, there will be probably new requirements that are to be fulfilled. And institutions usually rely on the commercial tools. I mean, like for many of the problems in many institutions, I mean, the local and the kind of government level, they mainly use the already kind of proved software. I mean, MIC is the standard in most of the German federal states and is being used in the whole MIC family. But some of them have their own developments or using some other tools and software. And so there is still a potential of for need of a tailored approach, which also opens the possibility to explore maybe different techniques and technologies to improve some of the functionalities and features. And data issues and order of magnitude to be considered is sometimes I'm always said, like depends on what we need this model for. I mean, we have to make sure that we are, working and developing models which serve the purpose. And very often it's what we said is this damage assessment of the potential damage is much, highly uncertain than the ones that we have from the hydrodynamic and hydraulic models. And of course, potential for digital twins and support by these institutions should be there. And I mean, I think we talk about potential development and placement, exploitation of the technologies that we have here. I think in Germany, there is a potential despite a very, very rigid bureaucracy. I mean, like when it comes to any kind of changes, I mean, the protocols, something which has been developed, but still, because there is a strong movement like everywhere in Europe, but also worldwide towards digitalization. So we are going into a digital twins era, also in German administration. So there is still a potential for exploring that, and also for the research to work on that. I would like, maybe because it's a final remark from my presentation, I mean, regarding really the case study, I concentrated on the case study. I would like to ask Zoran Vojinovic, maybe, if you want to wrap up. I mean, I left some minutes free if you want to say something and wrap up, not, I mean, in general, because I think presented a lot, and maybe to reflect on all of that before we get into the discussion and enter the question and answer session.
Well, I think there are several take-home messages from these lectures, from these presentations. One is that the models are very important and play a vital role in the water engineering. It's nothing new. It's already been like that for decades. Now with the new tools, new computational power and possibilities in the use of artificial intelligence, I think we can improve our capabilities. And I guess the scope for Artifact is really to look into these opportunities. And I think I see Zoran has switched on his camera.
No.
So I can, I would like to pass it on to Zoran and then to steer the discussion and questions.
Okay, thank you. Thank you, Natasa, for your lecture. Thank you for the remarks, Zoran. We are a bit ahead of time, but we have been going on with these two lectures for over an hour. So I would like to suggest a quick 5-minute break just to top up coffee or tea, and then we'll go with the final questions and discussion section. And we already have several interesting questions that have been asked. So let's get back at 30:35, yeah, in five minutes.
Because we have more time, eh? We can
say again.
Can we reconvene in 10 minutes?
I'm concerned that we're already losing some people.
Yeah. Okay.
I think 5 minutes is enough, just to grab a coffee or tea, and then if you need Zoran a bit more, don't worry.
No. I was just thinking that we are ahead of time. You mentioned, so I realize also that the schedule is a little bit. We are not.
Yeah.
But
let's come back in 5 minutes then. Yeah. Okay.
Okay.
I'm assuming people are back by now. But let's wait for another minute for everyone to rejoin. Thanks, Natasa. Glad to see I'm not alone here. Just talking to a screen.
Veljko is here. Zoran is also coming.
I'm around.
Yeah, Veljko is here as well. Okay, so let's start then the questions and discussion section. Zoran will join us in a minute, I'm sure. So the idea is, I'm proposing that we first address the questions that have already been posed by the people, and then we have some prepared topics for discussion later on, but let's see how it goes with the questions first. So Žarko Sretenovic, I can see you posted a couple of questions. Do you want me to rephrase those for you, or do you mind basically just asking the questions now for the benefit of everyone? Maybe I should rephrase the question. So the first question was, Žarko had a question about this direct rainfall or rainfall on grid approach as a simplification in urban flood modeling. And he's asking about the general opinion about using this approach. And then he says the idea is that when we apply rainfall directly to the 2D surface grid, it is no longer necessary to model the entire sewer network, which is hard, especially considering that most urban drainage systems are designed for a 2 or 5 year return period event. So for more intense storms, such as a 100-year rainfall event, the pipe network is quickly overloaded and overland flow becomes dominant. So based on our experience, is this a valid approach for modeling extreme urban floods? And what do we see as the main advantages or limitations of using this method? Does any of the speakers want to address this? Yes, Zoran?
Yeah, I think it's a very good question. And thank you for raising it up. Traditional way of modeling rainfall in 1D, 2D models has been through the use of hydrology in 1D model. And and basically you model rainfall runoff. The water goes through the pipe network system, then gets a surcharge. The water comes out from the pipe network system onto the ground and starts propagating. But that's actually not how it happens in real life. In real life, you have water falling normally on the ground, falling onto the houses. Then from the houses goes through the downpipes and goes into the pipe network system. So you suggested that maybe the other way should be to model or to simulate rainfall in the 2D model, in which case the simulation of through the 1D model is not necessary. I would not go with that approach. I would really combine it. I would use the for the areas which are housed, we have a housing and buildings and all of that. I would potentially connect them to the 1D model, and all the other areas could be modeled directly in a 2D model. That is maybe that's my opinion. That's how I would combine the two. I would do the 2D model rainfall, but also 1D model for this where there are direct connections to the sewer system. But you are right. The traditional model is not how it happens in reality.
Thanks, Zoran. Yes, if I can add to that, I mean, I have a couple of comments about this. One is, I agree, you should always try what Zoran suggested first. But then, if you want to use a simplified approach, try and see what kind of outputs the simplified model produces relative to the better model, to the more kind of logical model. And then if the two results are not that different, then you may use a simplified model. This could be very useful if you have to do repetitive model runs. It may pay off to go down this route. The other thing is I would like to mention is you mentioned here that most urban drainage systems are designed for a 2 or 5 year return period. That depends very much on the country and within the country. I can tell you that the standard of protection in the Netherlands, yes, is 1 in 2 years, occasionally 1 in 5 years. But in the UK, where I lived and worked for a long time, the standard is 1 in 30 years. There are cities and there are parts of the world around the world where the standard is 1 in 100 years. Basically, the more expensive the content that you are trying to protect from flooding, the more it pays off to invest in higher level of standard protection standard upfront, because this causes less damage afterwards, unless it's regulated as it is in some countries with technical guidelines and rules that you have to follow. So this can be very, very different. But the main advice is really, if you need a simplified model, especially if you're going to do some repetitive analysis during optimization or some uncertainty assessment or similar, build a real model first, see how the two compare, and then if you get that the simplified model works reasonably well, then you can use it. But don't just do that model on its own. And before I ask anyone wants to add anything to this? I think Jaco had a related question, or maybe let's first ask the question by Lorena. She says, thanks for the presentations. I have a quick question regarding pluvial modeling. How do you approach cases where the subsurface drainage network, such as stormwater pipes and manholes, is unknown or poorly documented, particularly in flat floodplain areas where surface flow patterns are also difficult to determine? Does anyone have any experience with this?
Well, the simplest answer would be go and survey it. I mean,
that was going to be my advice as well. Go out and measure and see what's going on. But because otherwise you're really walking in the dark. You don't know what is going on.
Yeah, agree.
Anyone has any other advice they would like to offer? I mean, I can say, yeah, it can be time consuming, it can be expensive, but it ultimately pays off to go out and inspect and survey and collect data.
I can quickly add. So since this is also AI the seminar, so it depends if you have a lot of flood maps, or you can quickly design some preliminary flood maps. You can design some easy models that match with the existing flood maps that you can get from local councils or consultants or or government official flood maps. There are some simple ways to train computer vision models to recognize different levels of flooding in these flood maps. You do need decent subset of flood maps to train the models, but we have been playing with this approach, and some other researchers have been trying this. It does depend. If it's a relatively flat area, it works well in a more steep areas of the city or more urbanized areas of the cities. Sometimes the approach doesn't work as well, but it's worth a try.
Thanks, Veljko. That's actually a good point. Yes, this way you can bypass the development of physically based model that we mainly talked about today, because you can go for the AI to straight estimating through. But the thing with this is that you would need quite a few flood maps to be able to effectively train the method, and this is where usually the trouble starts, based on my experience. But it's possible. There are ways to do this in a simplified way as well. Okay, the next question was also by Žarko. He says, I think it's similar to this one. What about underground infrastructure such as underpass, tunnels, or culverts that is not captured by LiDAR data? These features can be critical for correctly representing flow paths and flood behaviors in urban areas. In your experience, what is the best way to incorporate such infrastructures into a 2D surface model? I think we kind of already mentioned this, that you need representation of these subsurface elements in the model. This can't be captured by LiDAR data. Indeed, you have to go out and survey or look for existing data, or if you want to bypass this altogether for flood depth estimation or something like that, then maybe use an AI approach if you have sufficient other data. Does anyone wants to add something to this? Or?
Well, in terms of computation, you would normally incorporate this into 1D model rather than a 2D model.
Yes, yeah.
So,
or a combined 1D, 2D. But yeah, what happens underground needs to be, yes, indeed, in a model, and it's typically a 1D model. Because the flowing pipes is really predominantly 1D in nature. Okay, we have a question from Marko Radojic. He says, is it possible to use methodology of variable autoencoder used in stable diffusion as a way of teaching the model about spatial and time series data points, taking into account discretization in multidimensional tensor capabilities available in GPU hardware and distributed compute? It's a quite technical question. Does anyone want to answer this?
You went fast. Can you put it on the, where can we read it? It was a bit.
It's in the chat, yeah. So this is really about using the variable autoencoder, which is a kind of machine learning type method in stable diffusion as a way of teaching the model about spatial and time series data points. He's really talking about the development of machine learning based method, AI model for predicting depths and so on. So is it possible to use the methodology of variable encoder as a way of teaching the model about spatial and time series data point? I have to say I haven't tried this myself. I don't have any specific device about this. I guess the best advice is try and see how it works. That's what often is the approach in AI based on my limited understanding. Ben, do you want to add something?
I can just quickly add, we haven't tried with variable autoencoder, but we've been playing around with different convolutional neural networks and different models. I can't remember now which architecture. There's a Grujo, can you help me which architecture we used? Is there, Grujo?
Yes, just to find the unmute button. Actually, now we try with the classic encoder network. Actually, that is the part of the UNet and the SegNet architecture. Yeah, that is not variable autoencoders.
And we're still preparing some input data and playing around with that. You have to have a really good input data. Like, I mean, obviously the model takes everything, but rubbish in, rubbish out. So we've been playing around with some dirty data, and the method works. Yeah, we'll be working throughout this project. We'll be working on perfecting and trying different methods, especially different CNN configurations for this. But yeah, thanks.
Thank you.
Maybe if I can
I
add
think
yeah, Zoran, do you want to say something?
I want to say something.
Milan wants to say. Please go ahead.
Thank you. I think that diffusion model is the state-of-the-art models apply in different kind of science, and also should be used for flood modeling, because it can capture both domain, time and spatial domain. The limitation of application and development of this model is the output data needed for physical models. And these models should be also used with another ML-based alternatives for capturing both time and spatial domain.
If I may clarify on my question.
Yeah, please.
Actually, I wanted to ask, I mean, this was the question, but one thing that really inspired me to ask this question was the software Calypso, where we can map different damage types to different layers. And then that reminds me of the layered structure of a deep learning mechanism, and variable autoencoder can handle that very well, but it does need to have good calibration, good data, and the evaluation data set. So it's still speculative, but the compute needed compared to infrastructure to gather data is ridiculously inexpensive now. So, I mean, it might make a viable contribution to the effort. I come from a triple background, so I used to be a physicist and not really, never graduated that, but I code a lot and do AI, so like a hobby.
Thank you, Mark, for clarification. I mean, the only thing I can add to that is along the lines of what Greg already mentioned. My experience with AI applications in water engineering in general, not just flooding, is that you can go with sophisticated models as much as you want, but if the data is not up to the standard required, you won't get much out. And in those situations where you have insufficient data or data of not the best quality, at the end of the day, it doesn't really matter, you know, whether you use this deep learning or that deep learning. They're likely to give you similar kind of level accuracy models and so on. The differences become really important when you have a lot of data and a lot of good quality data, then you can start refining things and making things slightly better.
Yes, thank you.
Okay, it looks like there is a question by Yasmin. She says, I have a question regarding model resolution. How do we balance between the availability of data and the desired level of spatial detail when we are choosing the appropriate scale for a flood or urban planning model? Maybe this is a question for Zoran or Natasa.
Well, that's again another very good question. It's I think the choice, the selection of the resolution will come from the need of the model. If the model needs to be used for, I don't know, real-time prediction and early warning systems at the urban finite level, then you will need very high resolution. If you are using a model to kind of give you a high-level scanning assessment of the potential problems and potential measures that might be beneficial, then you can go with a coarser resolution. But yeah, I mean, depends what the purpose is, and then accordingly you need to invest in either high resolution data or go along with some lower resolution. But I think that will be my answer.
I mean, I can also just agree with that. That also shows the experience that we had, and also showing different examples where sometimes, like what Zoran had, where you really have to give an answer on a particular case or a specific location. Like then you need a high level, but for the preliminary risk assessment, you don't need very precise models and tools. Like it can be cool.
Yeah, if you're designing structure or something, then the high resolution is better, of course.
Yeah.
It's a scanning. Yeah. All right.
But that's a general approach, kind of, build a model that is fit for purpose. Milan wants to say something. Please go ahead.
Thank you. Veljko included me in discussion previously. I want to say that I am the member of Green AI group from Institute for Artificial Intelligence. Just want to express my gratitude for the incredibly interesting lectures, and the knowledge that you shared was extremely useful. And I have one question about dynamic simulations. It is possible to have continuous outputs from physical models.
What do you mean by continuous output?
I think that Milan prefer the outputs of physical models need to be continual and long hydrological time series needed for development of machine learning model. Because
I mentioned in one of my slides, I had that the typical simulations for flood purposes, flood management purposes, it's kind of event-based simulations. You can either use design storms or you can use some actual storms, but that typically would not exceed 2 or 3 days. But if you go to sewer systems simulations, particularly if you go analyzing overflows, and for the overflows we need to perform some statistical analysis, then you would run maybe 10 years of continuous simulations, and the physical-based models are very much suited for that. I have used them for the analysis of wastewater overflows, and then the only thing is, yeah, and they are also convenient because you can set the range of magnitude, so the computation can go through each and every time step for the low flows and for the high flows, or you can set it up that for certain flows it can jump across the computation and go and start computing only for the higher flows, and then it would kind of reduce the time. But in principle, yes, you can run continuous long-term simulations. I did run these type of things for 10 years duration, 5-minute time steps and things like that.
Yeah, indeed.
That would be a great source to train the AI models. Yeah,
it would be, definitely. Okay, any other questions? I don't see any in the chat. If not, I have a question for the rest of you. Some software has been mentioned in the presentation, Mike, series of software by DHI. I think Zoran mentioned SWMM as well, and so on. I was just wondering, does anyone has any example of other software being used in their organization for flood modeling? We would be keen to learn. Yes, Bentley Systems is kind of expanding. I'm pretty sure Innovize is expanding with its products, InfoWorks and the rest. Just keen to find out if someone else has been using other piece of software for flood modeling and if they are, satisfied with it, what they think about it. Yeah, Žarko says that Jaroslav Černy Institute to be used Mike Plus. Good. And how is it working for you? Okay, Žarko just says he's very satisfied. Fine. That's a nice way to answer shortly. Okay. Is anyone aware of any other emerging software Is there any open source software for flood modeling that people have been using? I know there are 1 or 2 extensions of SWMM and so on, but open source HackRAS. Okay, that's interesting. I've used HackRAS a long time ago when I was doing river engineering, but I didn't realize it became open source meanwhile. It's free to use, I know that, but open source in a sense that community is contributing to it, to the development, or just free to use? Okay, we have also a comment from Carlo. I happen to know Carlo because he's a former MSc student. Carlo works for the engineering agency of Rotterdam municipality in the Netherlands. He says, thank you for the presentation. I was wondering whether any of the presenters have experience modeling groundwater inflow. Here in the Netherlands, most unpaved areas have perforated drainage pipes to maintain groundwater tables, and these are typically connected to the main combined sewer system. Observed data clearly shows a slow system response after rainfall events, which suggests delayed inflow from groundwater. Do you have any ideas or recommendations on how to model this at a citywide scale?
Yeah, I can answer from my experience. I have used for INI studies, inflow infiltration studies, quite a lot. Again, it's a DHI software, and what matters there to look into these kind of processes is the hydrological module. And for that, DHI has developed, it's called RDII, so rainfall dependent inflow infiltration module, and that one is particularly good for modeling it has about 16 different parameters and looking into different subsurface processes and all of that. The only more complex than that is the Mike Shee version that can be used. But RDI is a standard tool used by DHI, within DHI software for modeling inflow infiltration, and it's pretty good. And you can get a pretty fair model results, and also calibration results with that software.
Thank you. Yeah, my only advice in addition to that is, as Carl already knows from his own MSc projects, is that groundwater modeling is a rather specialist area. So it might be a good idea to involve someone who knows that, in addition to describing flowing pipes and the rest. So it might be a good idea to talk to someone who is a groundwater specialist about this as well. Okay, we have Veronica just mentions Telemark. Is that the software you are recommending, Veronica? No? Are you around? Don't be shy. You don't have to switch on your camera. You can just talk. Oh, you're saying yes, it is open source.
Yes, we are also using Telemark. I mean, that's so together with Calypso. That's something.
Okay.
Okay.
Good. Anyone has any other experiences with software or any other issues they would like an advice on in terms of physically based modeling? I've noticed that quite a few utilities seem to be converting to InfoWorks. It's probably something to do with their marketing approach and the service they provide. I know that at least in the past, they used to provide quite a lot of support for modeling. So if you embark on a modeling exercise and you get stuck, they won't just sell you the software. They will help you basically develop a model and so on, if you buy the right package, of course. Okay, if not, we do have a few other topics to have a look at. One of the questions that, yeah, go on. Who was that?
There's one, Shangun Gang.
Oh, Shangun Garg. Okay, hi. Hi, Jangun. I think we are going to meet tomorrow. You will believe a new PhD student at University of Ljubljana, and I'll be in your PhD committee. You are doing PhD in remote sensing on evidence-based, nature-based water solutions using satellite remote sensing. I haven't used it myself, but saw a few posters DCGU using Delft 3D modeling. That's okay, but what is your question? Is this just a comment or? This could be a different Shangu. Yeah, sorry, not sure. Okay, one of the questions that Institute for Artificial Intelligence was keen on addressing as part of this discussion was which areas of flood modeling do you believe can be improved by the integration of AI and machine learning models? Veljko, do you want to clarify what is meant by this, by integration? Integration of AI with physically based models or something else?
I mean, we already touched upon that with some of the previous questions, that we can do 2D surface flood detection using some computer vision methods. So, I mean, in that regard, because once, obviously, the training is painful. I mean, training of the model, of the AI model is painful because of the data scarcity. But once trained, I guess these could give you a very rapid estimate of the flood extents and do quick predictions of the flood extents as well. But I was wondering if others had some examples. For example, I haven't really thought much about the subsurface issues and the groundwater issues and how AI or AI models or neural networks or deep learning can help with these subsurface issues, because these are very complex mathematical problems as well. But maybe someone has some idea on how AI can do that, because our main principles are integrating, going 1D, 2D, coupling 1D, 2D, and then trying different temporal machine learning models for both 1D and 2D. And
yes.
Yeah.
Yes, that's integration, but I kind of assume that would be about hybridization as well. We haven't talked really about hybridization of the physics-based models and AI. What you talked about is using AI instead of physically based model.
Yes, I mean, yeah, that's the other one. Yeah, the physics-informed neural networks is the other thing we are.
Or any form of hybridization, any using AI to improve the predictions of physically based models or the other way around. Does anyone have any experience with this? Or?
Maybe you can give us some more ideas on how to get this done better.
Marco says he can quote Professor Jan LeCun. Yeah, go ahead, Marco. Switch on your microphone and do the quote.
Well, what they actually claim is that large neural networks advanced enough to be almost sentient in a physical world, trained on video and data from sources like satellites, develop intuitively almost understanding of physics. If we work back through those steps, they will not share that technology with anyone probably anytime soon. But if we need to detect large amounts of data about groundwater, we should think about ground-penetrating satellite imagery and train the models on that. That's like, if NVIDIA aims to create Earth 2, we can create a sentient city eventually.
Yeah. Yeah, I mean, I agree with you. The more data we keep collecting and then creating, the more we can go in the direction of data-only models. But there will still be value. I would like to think in physically based models, and
Yes,
possibly,
definitely.
the integration between the two will be a necessary step in transition to
Yeah.
these more detailed models,
agree.
which will come in the future at some point.
Yes.
But I don't think we are at that stage yet. We don't have the kind of data in water engineering that people have in financial industry or in biosciences or elsewhere. Okay, Carlos says during ICUD conference, that's the International Conference Urban Range, which was held in Delft last year. I saw a study that used AI, convolutional neural network, to estimate flood depths based on camera footage and the vehicles on the street using e.g. wheel height as a reference. Yes, thank you for sharing that, Carlo. I think we have all witnessed this kind of work. This is not the only work along these lines. We had at TU Delft few projects along these lines as well. People are trying to use AI to estimate flood depths from all sorts of different videos, photos, often collected by ordinary people and shared on social media or otherwise. So this has been going on. This is just one more application of computer vision and AI. Okay. Does anyone has any other burning questions, either related to the presentations we saw earlier or otherwise? We have been going on with this discussion for about 35-40 minutes. Clearly, this is only a first training session out of 6, so there will be plenty of other opportunity to further discuss these things, especially discuss AI more in the future. This time we focused on physically based models. So if you don't have any questions, any further questions, perhaps we could wrap up now. Veljko, is there something else you would like to discuss, or Milan, or anyone?
Not really discussed. I just so I want to invite everyone to the next one that we haven't scheduled the exact date yet, but it's going to be in October, November, the next expert training. And that one, as you said, Zoran, it's going to focus more on AI-based flood risk assessment methods. So we're going to look into some of the how we can use some satellite images, of some studies that have used satellite images for flood detection. We'll look into the fluvial and pluvial, because there's not a lot on pluvial, so we have to branch out our knowledge. So we can use different methods from fluvial flood estimates as well. But yeah, you'll get information beforehand, a couple of months beforehand, about the next training. And for this session, as I said at the beginning, so we have recorded this session. We're gonna chop it up nicely and put it on YouTube. So for the link to the YouTube is going to be on the website, and we'll also send it to all the registered participants of today's session. So you can, if you miss some bits, it's been a very exhaustive and really thorough lecture today. So I'm sure you want to revisit some of the points that Zoran and Natasa have made. So the video is going to be online next week or the week after, the latest. Yep, I think that was all that I wanted to say.
Okay, thank you. So I guess in that case, yes, I think that provides a nice point where we can stop. So I would like to just thank all the presenters today and all of those who took part in the discussion. Hopefully you found something useful. If you have other burning issues you would like to discuss, write this down, please. Follow us on social media and on the website, and we'll let you know when the next training session is up. We will be organizing a summer school in first week of July in Novi Sad as well, which again is dedicated to the same topics. And if you think a summer school could be appropriate for you, feel free to register and to join. Again, you can find the details on the project website. Thank you once again very much to everyone involved, and yes, see you next time.
Okay,
Thanks, everyone.
thanks a lot.
Thank you. Thank you. And
Bye-bye.
bye.